Hello there, and welcome. I am so glad you found your way here tonight. Really, I am. Whatever brought you to this moment, a long day, a restless mind, a body that needs permission to stop, I want you to know that you are exactly where you need to be. You made it here. You can set everything else down now. The emails, the conversations, the things left unfinished, the quiet worries that follow you from room to room. None of that needs your attention tonight. You have nothing to do tonight but rest. Tonight, we are going to drift through one of the most ancient and quiet processes in the entire universe, the birth of stars. Not with urgency or excitement, but slowly, the way starlight itself travels, patient and unhurried across distances so vast, they quiet the mind just to think about them. Somewhere out there, right now, in cold clouds of gas and dust that have been drifting through the dark for millions of years, new stars are being born. Slowly, silently, without anyone watching. We are going to watch together tonight. If these calm journeys through the cosmos help you unwind and find your way to sleep, consider subscribing. There are many quiet nights ahead, and we would love to share them with you, one sleepy soul at a time. Now, let us begin. Stars are not born from nothing. They are born from the oldest material in the universe. Long before any sun existed, before any planet formed, before any ocean filled or any living thing drew breath, the universe was thick with clouds of hydrogen gas. These clouds are the raw material of everything that shines. When you look up at a star, you are looking at ancient hydrogen that was pulled together by gravity, compressed until it grew so dense and so hot that it ignited. Every star, including our own sun, began as a cold, dark cloud drifting quietly through space. Nothing about that beginning felt like light. Nothing about it felt like fire. It was slow and dark and patient, the way all beginnings are, before anything knows it has begun. Even ancient darkness, given enough time, will find a way to burn. Gravity is the architect of every star that has ever existed. It is not dramatic. It does not announce itself. It simply pulls, gently, persistently, without ever stopping. When a cloud of gas and dust becomes slightly denser in one region, gravity begins to draw more material toward that region. Slowly, over thousands or millions of years, that density grows. The cloud contracts. It begins to warm. The center, where the pressure is highest, grows hotter. This slow collapse is not violent. It is patient. Astronomers call the collapsing center a protostar, and it can take 100,000 years or more before that dense, warm core becomes anything like what we would recognize as a star. Gravity does not hurry. It has all the time in the universe, and it uses every moment of it. There is something deeply quiet about the way the universe builds its lights, one slow pull at a time, in the dark. The clouds where stars are born are called nebulae, and they are among the most beautiful structures in the known universe. The word itself comes from the Latin for mist or cloud, and that is exactly what they are: vast, slow-moving regions of gas and dust, hundreds of light years wide, so thin in places that the space inside them is closer to a perfect vacuum than anything we can create on Earth. And yet, they are not empty. Hydrogen, helium, traces of carbon and oxygen and silicon drift through them like breath through a cold room. When we photograph nebulae with powerful telescopes, they glow in greens and pinks and deep blues, not because they are lit from within, but because the radiation of nearby stars excites their gas, causing it to emit light. They are quiet, glowing, ancient. They are the places where everything luminous begins, a quiet drift in the dark, and slowly, something begins to glow. Some nebulae are so large they make the concept of size difficult to hold. The Tarantula Nebula, located in a neighboring galaxy called the Large Magellanic Cloud, stretches across nearly 1,000 light-years of space. If it were placed where the Orion Nebula sits, relatively close to us, it would cover a quarter of the entire sky and be bright enough to cast shadows on the ground at night. Most star-forming nebulae are smaller, but they are still deeply vast in any human sense of the word. Our entire solar system, all 8 planets and the Sun, and every comet and asteroid and ring of debris, would be a nearly invisible speck inside even a modest nebula. We are small. The places that made us are unimaginably large. That thought, held gently, can do something useful for the mind that is trying to let go. We are small, and the universe is patient with that smallness. Not all clouds collapse to form stars on their own. Sometimes they need a push. Astronomers have found evidence that many star-forming events are triggered by shock waves. When a nearby massive star explodes at the end of its life in what is called a supernova, the blast wave travels outward through space and compresses nearby clouds of gas and dust. That compression can be enough to push a cloud past the threshold where gravity takes over, beginning the long, slow collapse toward a new star. So in a very real and quiet way, dying stars give birth to new ones. The death of one sun sends a ripple through the dark that, millions of years later, ignites another. It is a cycle so old and so continuous that the universe has never truly gone dark since the first stars formed, more than 13 billion years ago. Every ending, given time, becomes a beginning somewhere else in the dark. The very first stars in the universe were nothing like our sun. They formed when the universe was only a few 100 million years old, from clouds of pure hydrogen and helium, the only elements that existed at the time. Without heavier elements, these clouds cooled differently, and gravity was able to pull together far more mass before the heat of compression stopped the collapse. The result was stars of enormous size, perhaps hundreds of times the mass of our sun, blazing with an intensity we have never directly observed. Astronomers call them population 3 stars. None of them survive today. They lived short, violent lives and exploded, scattering the first heavy elements, carbon, oxygen, iron, into a universe that had never contained them before. Every element heavier than helium that exists anywhere in the cosmos was forged inside a star. The first stars burned so bright they changed the universe, and then they were gone, quietly leaving everything behind. Deep inside a collapsing cloud, as pressure and temperature rise, something remarkable begins to happen. At a certain point, roughly 10 million degrees Celsius, hydrogen atoms are moving fast enough and are packed closely enough that their nuclei begin to fuse together. 2 hydrogen nuclei merge to form helium, releasing a burst of energy in the process. This is nuclear fusion, and it is the engine of every star. The energy released pushes outward against the inward pull of gravity, and for a time, these 2 forces reach a balance. The star settles. It becomes stable. It finds a kind of equilibrium that can last for billions of years. Our own sun has been in this balance for about 4.5 billion years. It is not rushing. It is simply burning, steadily, in the dark, as it has done for longer than the Earth has existed. A slow and ancient balance, held without effort, for billions of years. Before a star ignites, it passes through a brief and tender phase called the protostellar phase. The collapsing core of gas has grown warm and dense, but fusion has not yet begun. The object at this stage is called a protostar, and it glows not from nuclear reactions but simply from the heat of compression, the same way air grows warm when you press it quickly in a bicycle pump. A protostar is surrounded by a spinning disk of gas and dust, the leftover material from the original cloud. Some of that material will fall onto the protostar and feed its growth. Some will eventually form planets, and some will be blown away when the star finally ignites and sends its first winds outward through the surrounding cloud. As you rest tonight, somewhere in the Milky Way, hundreds of protostars are quietly warming in the dark. Warm, not yet burning, waiting without knowing. A light that does not know it is a light yet. The disk of material that surrounds a young star is called a protoplanetary disk, and it is where planets are born. These disks are flat and spinning, shaped like an enormous, slow-moving record of gas and dust, orbiting the new star. Over millions of years, the particles within the disk collide and stick together, forming larger and larger clumps. Pebbles become boulders, and boulders become small bodies called planetesimals. Planetesimals collide and merge into protoplanets. The process is slow and largely silent, a gradual accumulation of material through billions of gentle impacts, spread across a disk that may span hundreds of millions of miles. Our own Earth was built this way, grain by grain, collision by collision, over about 50 million years. The ground beneath you tonight was assembled slowly, in orbit around a young sun, from the dust of a collapsing cloud. Everything solid began as something scattered, drifting, and very, very small. Young stars are not quiet. In the first few million years of a star's life, before it has settled into the long calm of its main sequence phase, it is active and turbulent in ways that shape everything around it. Newly formed stars often emit powerful jets of material from their poles, thin streams of gas that shoot outward at hundreds of miles per second, carving through the surrounding nebula. These jets, called Herbig-Haro objects, can extend for light years in both directions, and are among the most visually striking features of star-forming regions. At the same time, the young star releases intense radiation and stellar winds that slowly blow away the remaining gas and dust of the original cloud, clearing the space around it. Eventually, the nebula thins and dissipates, and the new star stands alone in the dark, its light reaching outward for the first time without obstruction. Every young light goes through a period of restlessness before it learns to shine steadily. Stars form not just alone but in clusters. When a large nebula begins to collapse, it does not condense into a single point. Gravity creates multiple centers of collapse within the same cloud, and dozens or even hundreds of stars can form at roughly the same time from the same original material. We call these open clusters, and they are scattered throughout the Milky Way. The Pleiades, the small gathering of blue stars visible to the naked eye on winter nights, is one such cluster. Roughly 1,000 stars that formed together from the same cloud about 100 million years ago. Over time, the gravitational interaction between stars in a cluster and the tidal forces of the galaxy slowly pull the cluster apart, and the stars drift away from each other over hundreds of millions of years. They were born together, and they drift apart, slowly and quietly, the way many things do. Born together from the same breath of cloud, they drift apart across the ancient dark. The color of a star tells us its temperature, and its temperature tells us almost everything. Blue stars burn hottest. Their surfaces can reach 40,000 degrees Celsius or more. White stars are somewhat cooler. Yellow stars, like our Sun, sit in the middle range, with surface temperatures around 5,500 degrees. Orange stars are cooler still, and red stars are the coolest of all. This sequence of color and temperature also tells us about a star's life. Blue stars burn through their fuel so quickly that they live only a few million years, brief, brilliant, and gone. Red dwarf stars burn so slowly and so faintly that the coolest ones may live for trillions of years, far longer than the current age of the universe. Our Sun sits in a calm, comfortable middle, with a lifespan of about 10 billion years. It is neither rushing nor lingering. It is simply burning at a pace that suits the quiet work of sustaining a solar system. A slow burn is the longest burn, quiet and steady, across all the years of the dark. Most stars in the universe are not like our Sun. The most common type of star is the red dwarf, a small, cool, dim object that burns hydrogen so slowly that it will outlast almost everything else in the cosmos. Red dwarfs make up roughly 70 to 80% of all stars in the Milky Way. They are so faint that none of them are visible to the naked eye from Earth, even though the nearest star to our Sun, Proxima Centauri, is a red dwarf only 4 light-years away. What is remarkable about red dwarfs is not what they do, but how long they do it. A red dwarf of 1/10 the mass of our Sun could burn for 10 trillion years. When the universe is that old, 1,000 times older than it is today, red dwarfs will still be quietly glowing in a cosmos that has gone otherwise dark. Even now, as you drift, those faint and patient stars are burning slowly in the dark, waiting for a universe that has not yet grown old enough to need them. Binary star systems, 2 stars orbiting each other, are more common than single stars like our Sun. Astronomers estimate that more than half of all stars in the Milky Way are part of binary or multi-star systems. In some cases, the 2 stars orbit each other from a great distance, so far apart that a planet could comfortably orbit one of them without feeling much gravitational disruption from the other. In other cases, the stars are close enough that they pull material from each other, creating complex flows of gas between them. There are even contact binaries, pairs of stars so close that their outer layers actually overlap, forming a figure-8 shape as they orbit. Most binary systems are calm and stable over long periods, 2 stars circling each other across the years in a slow and gravitationally balanced dance that can last for billions of years. 2 lights circling each other across the deep, patient dark, a slow and ancient waltz. The nearest star-forming region to our solar system is a nebula called Rho Ophiuchi, located about 450 light-years away. In cosmic terms, it is essentially next door. Astronomers watch it closely because it offers one of the clearest views of active star formation available to us. Within its glowing clouds, dozens of young stars have recently ignited, and the region is rich with protostars still in the process of collapse. When we photograph Rho Ophiuchi, we see a dense and colorful tangle of gas and dust, glowing in pale blues and oranges, threaded through with dark lanes of cold, thick material that has not yet been illuminated by a nearby star. It is one of the most beautiful things our telescopes have ever revealed, and it is happening silently, slowly, across hundreds of light years, while we sleep and breathe and turn in our beds. The nearest nursery of stars is just next door, quietly making lights in the dark. Not every protostar successfully becomes a star. Some collapsing clouds do not accumulate enough mass to reach the temperatures required to ignite nuclear fusion. These objects, called brown dwarfs, are sometimes described as failed stars, though they are far more interesting than that description suggests. Brown dwarfs are warmer and denser than planets, and they glow faintly with the heat of their initial compression. But they cannot sustain fusion, and so they slowly cool over billions of years. They are common, perhaps as common as true stars, but they are so dim that we can barely detect most of them. A brown dwarf cools to the temperature of a warm oven over a billion years, and then continues to cool, slowly, for trillions of years after that. They are patient objects. They asked to be stars, and the universe said, not quite, and they went on glowing anyway, quietly, in the spaces between the lights. Not quite a star, not quite a planet, something patient and dim, cooling slowly in the dark. The Orion Nebula is the most studied star-forming region in the sky, and one of the few nebulae visible to the naked eye. It sits in the Sword of Orion, that familiar winter constellation, and on a dark night it appears as a faint smudge of light below the 3 stars of Orion's belt. Through a telescope, it reveals itself as a vast and glowing cloud of gas, illuminated by a tight cluster of young, hot stars at its center. These 4 central stars, called the trapezium, are only about 100,000 years old, newborns in stellar terms. Their radiation is slowly eroding the surrounding nebula, and within the cloud, dozens more protostars are still forming. The Orion Nebula is not a relic of the past. It is an active, ongoing event, a stellar nursery in operation right now, tonight, 4 years of light away, turning cold gas into new suns, with slow and patient gravity. 4 years of light away, something ancient and gentle is still making stars tonight. When the first powerful wave of starlight and radiation from a newborn star passes outward through the surrounding cloud, it does something profound. The energy from the star excites the hydrogen gas in the nebula, causing the electrons in those atoms to jump to higher energy states and then fall back, releasing light as they do. Different elements release different colors. Hydrogen glows red and pink. Oxygen glows green and blue. Sulfur glows in deep reds and oranges. The result is the glowing, color-rich nebulae that appear in our most iconic telescope images. What we see in those images is literally the light of a new star being absorbed and re-emitted by the cloud that once held it. The nebula glows not from within, but because a new sun has just woken inside it. It is one of the most beautiful feedback loops in nature. A star, illuminating the very womb from which it was born. A new light wakes, and the cloud that held it quietly begins to glow. Stars are classified in a system so old and so deeply embedded in astronomy that we still use the letters assigned in the 1900s, even though they no longer follow any alphabetical logic. From hottest to coolest, the main spectral types are O, B, A, F, G, K, and M, a sequence astronomers remember with the phrase, "Oh, be a fine girl, kiss me." Our Sun is a G-type star, sitting comfortably in the middle of the sequence. O-type stars are the rarest and most powerful. They are dozens of times more massive than the Sun, burn tens of thousands of times brighter, and live only a few million years before exploding. M-type red dwarfs are the most abundant, the faintest, the slowest, and the most enduring. The same categories that describe things as different as a brief, blazing giant and a trillion-year candle, all held together by a single, quiet, ancient sequence of letters. In the vast catalog of lights, every star finds its place in a long and patient order. The relationship between a star's mass and its luminosity is one of the most fundamental patterns in astronomy. Larger stars are not just a little brighter, they are vastly, dramatically brighter. A star twice the mass of our Sun does not shine twice as brightly. It shines roughly 12 times as brightly. A star 10 times the mass of our Sun shines 10,000 times as brightly. This steep relationship means that massive stars burn through their fuel at a rate far beyond what their larger reserves can sustain. A star 30 times the mass of our Sun has roughly 30 times more hydrogen to burn, but it burns it millions of times faster, and so it lives only a few million years instead of billions. Size and brightness come at the cost of time. The quietest, dimmest stars are also the ones that will outlast everything. The brightest ones burn fastest. The faintest ones endure quietly. The dark rewards patience. The Hertzsprung-Russell diagram is one of the most important charts in all of science, and it is surprisingly simple to understand. Astronomers in the early 20th century independently noticed that when you plot a star's luminosity against its temperature, stars do not scatter randomly. They cluster in distinct regions. The long diagonal band where most stars sit, including our Sun, is called the main sequence, a region where stars are fusing hydrogen in their cores and have found a stable balance between gravity and radiation. Stars above and to the right are giant and supergiant stars, older and expanded. Stars below and to the left are white dwarfs, the dense, cooling remnants of dead stars. The diagram is a map of stellar life. It shows you not just what a star is, but where it is in its journey, how old it might be, and quietly, what will eventually become of it. A map drawn in light and temperature, telling the slow story of every star that ever burned. Our Sun formed about 4.5 billion years ago, from a cloud of gas and dust in one of the spiral arms of the Milky Way. It was not a first-generation star. The cloud from which it formed already contained heavy elements forged in previous generations of stars: carbon, oxygen, nitrogen, iron, silicon, the elements that would eventually become Earth and oceans and life. The Sun is what astronomers call a population 1 star, meaning it formed from enriched material and carries the legacy of many stellar generations before it. When the Sun ignited, its radiation and solar wind swept the surrounding protoplanetary disk, pushing lighter gases to the outer solar system and leaving rocky materials behind in the inner region. Everything that makes up the Earth, every rock, every drop of water, every atom in every cell of your body, was sorted and placed by the Sun's first breath. We are sorted stardust, placed here by the first breath of our own quiet Sun. The process by which hydrogen fuses into helium inside a star is called the proton-proton chain, and it is the same process that powers every hydrogen bomb ever built. Except that in a star, the immense gravity of billions of miles of gas above the core provides the pressure to sustain it for billions of years, rather than microseconds. In the Sun's core, roughly 600 million tons of hydrogen are fused into helium every single second. And yet, despite this rate of consumption, the Sun has enough hydrogen to continue burning for another 5 billion years. The core is so extraordinarily dense, about 150 times the density of water, that a photon of light generated in the fusion reaction takes about 100,000 years to slowly work its way from the core to the surface. The sunlight on your face left the core of the Sun long before humans existed. The light that warms us today began its slow journey before our ancestors walked the Earth. Around certain young stars, the protoplanetary disk does not all condense into planets. Some of the material forms comets, small, icy bodies in the outer regions of the solar system. Others form asteroids, rocky fragments in the inner regions. These bodies are not random debris. They are the material that was present but never incorporated into a full planet, left over from the same slow process of accretion that built the worlds we know. Comets in particular carry some of the most ancient and unmodified material in the solar system, ice and dust that has been in cold storage since the Sun's formation, 4.5 billion years ago. When a comet passes close to the Sun, that ancient ice sublimates and streams outward as a long, glowing tail. For a brief moment, we can watch material that formed with our solar system, slowly warming and dissolving, ghost-like, in the light of the star that made it. Ancient ice, patient across billions of years, slowly returning to the light that made it. 2 Tauri stars are the adolescents of the stellar world, young stars that have not yet stabilized into the calm, steady burning of full starhood. They are typically less than 10 million years old, and they are volatile and irregular in their behavior. T Tauri, star flares and dims unpredictably, casting off bursts of stellar wind and radiation. Its luminosity can vary by large amounts from day to day. Astronomers can identify T Tauri stars partly by this variability, and partly by the presence of surrounding disks of gas and dust that have not yet been fully blown away. Our own Sun was once a T Tauri star, roughly 4.5 billion years ago, and during that phase, it was probably 20 to 50% more luminous than it is today, blasting the early solar system with intense radiation. Everything on Earth today is here because the Sun eventually calmed down. Even the most restless young stars, given time, learn to burn quietly and steadily. The most massive stars in the universe are so large that the concept becomes difficult to hold. The largest known star, a hypergiant called UY Scuti, has a radius roughly 1,700 times that of our Sun. If you placed UY Scuti at the center of our solar system, its surface would extend out past the orbit of Saturn. Our entire inner solar system, Mercury, Venus, Earth, Mars, would sit entirely within the star's outer layers. And yet, despite its size, UY Scuti is not particularly massive compared to some other stars. Mass and volume do not always scale together. The most massive stars, called hypergiants, can be over 200 times the mass of the Sun. They are so massive that they are barely stable. They live turbulent, short lives, burning through their fuel in millions of years and ending in colossal explosions. Tonight, the universe is still making them, quietly, in the densest star-forming regions. Size beyond comprehension, burning too bright to last. Quiet giants of a short and ancient dark. When we observe star-forming regions with infrared telescopes, we can see through the dust that blocks visible light and watch protostars in the act of formation. Dust is opaque to visible light, but partially transparent to infrared, which has longer wavelengths that pass more easily through dense material. This is why some of the most important astronomical observations of the last few decades have come from infrared space telescopes, the Spitzer Space Telescope, and, more recently, the James Webb Space Telescope. Webb, launched in December 2021, has revealed star-forming regions in a level of detail never seen before, showing individual protostars embedded in their dusty cocoons, jets of material streaming from their poles, and protoplanetary disks in dozens of young star systems. We are watching stars being born in real time. The nursery is lit, and for the first time, we have the right kind of eyes to see inside it. We have finally built an eye patient enough to see through the dust, into the place where lights are born. The pillars of creation, perhaps the most famous astronomical image ever taken, are columns of cold gas and dust inside the Eagle Nebula, located about 6,500 light-years from Earth. The original Hubble image, captured in 1995, showed 3 towering pillars of dark gas, glowing at their edges where the radiation from nearby hot young stars was slowly eroding them. Embedded in those pillars were newly forming stars, still wrapped in their dusty envelopes, not yet fully lit. The pillars are roughly 4 to 5 light-years tall, meaning that if you traveled at the speed of light, it would take 4 to 5 years to go from base to tip. They are being slowly destroyed by the radiation of the stars they helped create. In a few million years, they will be gone. Tonight, they are still there, slowly dissolving in the light they helped to make. A patient structure, slowly taken apart by the very lights it gave rise to, quietly and without grief. The concept of stellar metallicity sounds technical, but its meaning is quietly profound. In astronomy, every element heavier than hydrogen and helium is called a metal, which means oxygen, carbon, nitrogen, iron, silicon, and every other element on the periodic table beyond the first 2 are all considered metals in the stellar classification system. A star's metallicity tells us what generation of star it is. The very first stars had 0 metallicity. They formed from pure hydrogen and helium, and when they died, they enriched the universe with heavier elements for the first time. Each subsequent generation of stars formed from slightly more enriched gas, and their deaths enriched it further. Our Sun has a metallicity of about 2%, meaning 2% of its mass, by number, is elements heavier than helium. That 2% is the legacy of billions of years of stellar births and deaths before us. We are the enriched generation, made from everything every star before us quietly left behind. The Carina Nebula, one of the largest and brightest nebulae in the sky, is a region of chaos and creation. Spanning more than 300 light-years, it contains some of the most massive and luminous stars known, including Eta Carinae, a binary system so massive and unstable that it may be on the verge of exploding. The Carina Nebula is actively forming new stars, while simultaneously being torn apart by the radiation and winds of its most massive residents. It is a region where creation and destruction happen simultaneously, where the birth of new stars is driven partly by the disruption caused by the deaths and outbursts of older ones. It is not peaceful in the way a quiet meadow is peaceful, but seen from a distance of 7,500 light-years, through the silent dark of space, it is still. It is ancient. It is just the universe doing what it has always done, slowly and without hurry. And even in regions of enormous energy, the vast distances of space reduce everything to a slow and ancient stillness. The James Webb Space Telescope has given us what many astronomers call the deepest look into the universe ever achieved. One of its first released images was a field of galaxies, each galaxy containing hundreds of billions of stars, many of those stars hosting planetary systems, all crammed into a patch of sky roughly the size of a grain of sand held at arm's length. In that single image, we are looking at light from galaxies so distant that it left them 13 billion years ago, when the universe was young. We are looking at the early universe. We are watching, in the photons that hit Webb's golden mirror, the very epoch when the first large structures of stars were forming. And all of this was captured by a telescope floating, cold and quiet, 1,000,000 miles from Earth, on the far side of our planet from the sun, slowly turning its ancient eye toward the dark. A cold, patient mirror in the dark, turning slowly, gathering the oldest light in the universe. The feedback between a forming star and its surrounding cloud is called stellar feedback, and it is one of the most important self-regulating processes in the cosmos. When a new star ignites, it does not simply sit quietly inside its cloud. Its radiation heats the gas around it. Its stellar winds push outward against the infall of new material. Its jets carve channels through the cloud. This feedback can slow or stop the formation of other stars in the same region, by heating the gas to the point where gravity can no longer pull it together. At the same time, the shock waves from stellar winds can compress other parts of the cloud, triggering new rounds of star formation nearby. A single star's birth can both prevent and cause the birth of other stars in its neighborhood. It is a system of balance, quiet and complex, and maintained without any intelligence or intention, the way all the best balances are. Everything in balance without knowing it is balancing, the universe maintaining itself, quietly, in the dark. Brown dwarfs were theorized for decades before they were finally confirmed. Astronomers had predicted in the 1960s that objects with less than about 8% of the sun's mass would not accumulate enough pressure to ignite sustained hydrogen fusion. But because brown dwarfs are so faint, confirming their existence proved difficult. The first confirmed brown dwarf, Gliese 229b, was not discovered until 1995. Since then, hundreds have been found, and we now understand that they span a wide range of masses and temperatures. The coolest brown dwarfs are so cold that water vapor and even methane exist in their atmospheres, making them more similar in atmospheric chemistry to giant planets than to stars. They exist in the gray zone between the two, too large to be a planet, too small to be a star, cooling slowly and quietly in the dark. Objects that almost were something else, patient, dim, cooling over billions of years, existing quietly in the space between what something could have been. The formation of a star is not a single event. It is a process that unfolds across timescales, nearly impossible to hold in the human mind. The initial cloud collapse takes roughly 100,000 years. The protostellar phase lasts another 100,000 to 1,000,000 years. The T Tauri phase, the turbulent adolescence of a sun-like star, lasts roughly 10 million years. Only after all of this does the star settle onto the main sequence and begin its long, stable life. If we compress the formation of our sun into a single human lifetime of 80 years, the initial cloud collapse would represent the first 10 years of life. The protostellar phase might be the teenage years. The T Tauri phase would last into early adulthood. Only around age 30 would the star settle into its long career of quiet, stable burning. The last 50 years would be the main sequence, steady, slow, and calm. A long adolescence before the steady work begins, and then, finally, a quiet and enduring light. Molecular clouds, the largest and densest structures in which stars form, are cold, extraordinarily cold. Their temperatures range from about 10 to 30 Kelvin, which is roughly -240 to 260 degrees Celsius. To put this in perspective, the coldest temperature ever recorded on Earth's surface was about -89 degrees Celsius. The cores of molecular clouds are more than twice as cold as that. This extreme cold is what allows these clouds to exist. At higher temperatures, the gas would be too energetic to remain gravitationally bound and would disperse. The cold also means that the gas molecules within these clouds move very slowly, and complex molecules, including organic molecules, amino acid precursors, and other compounds relevant to life, can form on the surfaces of dust grains without being immediately broken apart by heat. The cold, dark clouds of space are quiet chemistry labs, slowly building complexity in the dark. In the coldest, darkest places, the most patient chemistry quietly builds the pieces of everything. A phenomenon called the initial mass function describes a universal pattern in star formation that appears to hold across different galaxies and different epochs of the universe. When a batch of stars forms from a cloud, the distribution of their masses follows a predictable curve. Many small, low-mass stars, and only a few massive ones. This is not a coincidence or a local effect. It appears to be a deep feature of the physics of gravitational collapse and feedback. No matter where in the universe you look, star formation consistently produces roughly the same ratio of small stars to large ones. The universe has a preference. It makes mostly small, dim, patient stars. The bright ones are the exception. In the grand accounting of stellar births across cosmic history, the vast majority of lights the universe has ever made have been quiet, faint, and enduring. There is something gently reassuring in that. The universe, given the choice, prefers to make quiet lights that burn slowly and last a long, long time. Tonight, while you breathe slowly, somewhere between 10 and 15 new stars are being born every year in the Milky Way alone. Spread across the galaxy's hundreds of billions of star systems, this rate may sound modest, and it is, compared to the era of peak star formation roughly 10 billion years ago, when galaxies were producing stars thousands of times faster. Our galaxy has settled into a quieter phase of its life. The era of most intense creation is behind it, but stars are still being born. Dust is still collapsing. Protostars are still warming in their dark envelopes. The galaxy has not stopped making lights. It has simply slowed to a more contemplative pace, the way a long creative life eventually settles into something steadier and more deliberate than the frenetic work of youth. Even now, the galaxy is quietly making new stars, slowly, 10 at a time, in the long dark of a calmer age. The role of magnetic fields in star formation is something astronomers have been working to understand for decades. Molecular clouds are threaded with magnetic fields, invisible lines of force that run through the gas and resist compression. In some models, magnetic fields slow or even prevent collapse by providing a kind of additional pressure against gravity. Over time, a process called ambipolar diffusion, in which neutral gas slowly drifts across magnetic field lines while ions remain locked to them, gradually removes magnetic support from the densest regions of a cloud, allowing gravity to finally win. This process takes millions of years. The magnetic field does not surrender quickly. It holds back the collapse for a very long time, and only when the neutral gas has drifted far enough does the cloud finally begin its journey toward a star. Magnetic fields are patient resistors. They slow the birth of stars, one quiet field line at a time. Even in the making of stars, there is resistance, patient and invisible, yielding only slowly to the weight of time. Some of the most beautiful photographs in modern astronomy show what are called Bok globules, small, dark, dense clumps of gas and dust silhouetted against bright background nebulae. They were named after the Dutch-American astronomer Bart Bok, who studied them in the mid-20th century and suspected they were sites of active star formation. They were right. We now know that many Bok globules contain protostars forming inside them. They appear as dark teardrops or irregular blobs of shadow against glowing gas, dense enough to block all the background light. They range in size from about a light year to a few light years across. Inside them, in absolute darkness, the slow process of stellar birth is underway. The stars forming inside Bok globules will not be visible until they have grown bright enough to begin eroding their own envelopes. Until then, they are silent, dark, and private, forming in the deepest quiet. The most private births happen in the darkest envelopes, in a silence that no light has yet pierced. The concept of the gene's mass is the threshold at which a cloud of gas becomes gravitationally unstable and will collapse to form a star. Below this mass, thermal pressure, the tendency of gas to push outward as it warms, is enough to resist gravity, and the cloud will not collapse. Above it, gravity wins, and the cloud will begin to contract. The gene's mass depends on the temperature and density of the cloud. Colder and denser clouds have a lower gene's mass, meaning smaller overdensities can begin to collapse. This is why molecular clouds, being cold and dense, are the preferred nurseries for stars. The mathematics of the gene's mass were worked out in 1902 by the British physicist James Jeans, a century before we could directly observe the process he described. He calculated, with pencil and paper, the conditions under which cold, dark clouds of gas would fall inward and become stars. Long before we could see it happen, someone worked out in quiet numbers the weight of a cloud that would fall. The stellar nurseries of the universe are not silent in the way we might imagine. They are dark, but not acoustically quiet. Sound cannot travel through the near vacuum of space, it is true. But pressure waves, similar in structure to sound, do propagate through the denser regions of molecular clouds, driven by stellar winds, supernova shock waves, and gravitational interactions. These waves compress and rarefy the gas as they pass, and their effects on star formation are real and measurable. If you could somehow stand inside a molecular cloud, compressed by its weight, surrounded by darkness and cold, you would feel a constant, very slow pulsing as these waves moved through you. The birth of stars has a rhythm. It is not a sound we can hear, but it is a rhythm we can measure, and it is ancient, and it has been beating since long before our galaxy had finished finding its shape. An ancient rhythm in the dark, slow and unfelt, the pulse of a universe still making its lights. When a star, like our sun, finally exhausts the hydrogen in its core, something slow and dramatic begins. Without the outward pressure of fusion to resist it, gravity begins to compress the core further. The core heats up. The outer layers of the star, heated by the increased energy output, begin to expand outward, slowly at first, then more and more, until the star grows into a red giant, perhaps 100 times its original diameter. For our sun, this will happen in about 5 billion years. When it does, it will expand outward past the orbit of Mercury and Venus, and possibly past Earth. The surface of the expanded sun will be cooler and redder than it is today, but the total luminosity will be far greater. The sun's old age will be large and slow and red, a gradual blooming outward that takes hundreds of millions of years. Tonight, it is still young. It has a long life yet to live. Still young, still calm, still burning steadily. The sun has not yet begun to bloom into its long old age. The deaths of stars are, in some sense, more important to the universe than their lives. A star spends billions of years fusing hydrogen, slowly building helium. It then fuses helium into carbon and oxygen. In higher mass stars, this continues. Carbon fuses into neon, neon into oxygen, oxygen into silicon, silicon into iron. Iron is the end of the line. Fusing iron absorbs energy rather than releasing it, and the star, unable to support itself, collapses catastrophically in a fraction of a second. The outer layers fall inward and then rebound in a colossal shock wave, a supernova. In the intense heat and pressure of that explosion, elements heavier than iron, gold, platinum, uranium, are forged for the first time. Every atom of gold in every ring, every gram of platinum in every laboratory, was made in a star's violent last moment. The universe makes its heaviest elements only at the moment of greatest loss. The heaviest and most precious things are made only in the moment of ending, quietly scattered across the dark. Beyond the core collapse supernova, there is another kind of stellar death that has shaped the history of the universe in quieter but equally profound ways. When a white dwarf, the dense remnant of a sun-like star, is part of a binary system, it can slowly pull material from its companion star. If enough material accumulates, the white dwarf's core reaches the temperature and pressure needed to reignite fusion. Not gradually, but all at once, in a runaway thermonuclear explosion called a Type 1a supernova. What makes these explosions remarkable to astronomers is that they always release roughly the same amount of energy. This makes them what is called standard candles, objects of known luminosity that can be used to measure vast distances across the universe. It was by studying Type 1a supernovae in the late 1990s that astronomers discovered the expansion of the universe is not slowing down, it is accelerating. Something unknown is pushing the universe apart, faster and faster, quietly, in the dark. Even in death, some stars become rulers, measuring the dark universe with their own quiet light. The rest here, for a moment. There is more to come, and the universe is patient. So are we. Neutron stars are what remain when a massive star collapses and does not quite become a black hole. When a star between roughly 8 and 20 times the mass of our Sun exhausts its fuel and its core collapses, the outer layers rebound in a supernova, while the inner core is compressed to an extraordinary density. What is left behind is a sphere of neutrons, the densest ordinary matter in the universe, roughly 10 to 20 kilometers across, containing more mass than our Sun. A neutron star is so dense that a single teaspoon of its material would weigh about 10 million tons on Earth. It is not hollow or gaseous. It is solid and cold and impossibly compact, rotating in the dark, the leftover heartbeat of something that was once enormous. Some neutron stars spin hundreds of times per second. They do not announce this. They simply turn, in the dark, at a speed nothing in our daily experience can prepare us for. Something enormous collapses into something the size of a city, and quietly, it begins to spin. Pulsars are neutron stars with a particular geometry. They emit beams of electromagnetic radiation from their magnetic poles, and because they spin, those beams sweep the sky like lighthouse beams. If Earth happens to lie in the path of one of those beams, we detect a pulse of radio waves every time the beam sweeps past us, with extraordinary regularity. The first pulsar was discovered in 1967 by astronomer Jocelyn Bell Burnell, who noticed a repeating radio signal so regular that her team initially labeled it LGM-1, Little Green Men, as a half-serious placeholder, while they ruled out an artificial origin. The signal turned out to be a neutron star rotating about 30 times per second, and it was so perfectly regular that it initially seemed impossible for a natural object to produce. Some pulsars are so stable in their timing that they rival the best atomic clocks on Earth. A dead star, spinning in the dark, keeping better time than anything we have built. In the silence, after a star's death, something small and spinning keeps perfect time, patient and faithful in the dark. Magnetars are the most extreme objects in the known universe that are not black holes. They are a type of neutron star with a magnetic field roughly 1,000 times stronger than that of an ordinary neutron star. And ordinary neutron stars already have fields trillions of times stronger than Earth's magnetic field. A magnetar's field is so powerful that if one were placed at the distance of the Moon, roughly 250,000 miles away, it would pull the iron from every red blood cell in your body. They are not placid objects. They occasionally release sudden bursts of X-rays and gamma rays, called starquakes, caused by fractures in their rigid neutron-rich crusts. These bursts can release more energy in a fraction of a second than our Sun emits in 100,000 years. The nearest known magnetar is about 9,000 light-years away. At that distance, it is harmless, a distant pulse of extreme physics flickering quietly in the dark. The most extreme objects in the universe burn quietly in the dark, at distances that render them gentle as starlight. White dwarfs are the final state of most stars in the universe, including our Sun. After a Sun-like star expands into a red giant and gently sheds its outer layers as a glowing shell of gas called a planetary nebula, what remains at the center is the hot, dense core, a white dwarf. It is roughly the size of Earth, containing half the mass of the original star. It is no longer fusing anything. It is simply cooling, slowly, over billions of years, radiating the heat of its compression into the surrounding dark. A young white dwarf glows blue-white at temperatures of 100,000 degrees. Over billions of years, it dims and reddens. Eventually, theory predicts, it will cool completely and become a black dwarf, a cold, dark remnant, invisible and inert, drifting through the cosmos. No black dwarf has ever been observed. The universe is not old enough yet, and not one white dwarf has had enough time to cool completely. They are all still warm, still glowing, still fading, patiently, across timescales longer than anything that has yet occurred. Still cooling, still fading, still gently warm, waiting for a universe old enough to finally let them go dark. Planetary nebulae, the glowing shells of gas expelled by dying sun-like stars, are among the most geometrically beautiful objects in the universe. They form when an aging red giant sheds its outer layers in a slow stellar wind over thousands of years, and the hot white dwarf left at the center illuminates that outflowing gas with its ultraviolet radiation. The result is a thin, glowing shell of ionized gas, sometimes spherical, sometimes bipolar, sometimes with intricate rings or braided filaments that astronomers are still working to explain. The Ring Nebula in the constellation Lyra is one of the best-known examples, a cool, pale ring of glowing gas about 1 light-year across, surrounding a small, brilliant white dwarf at its center. It is the gentle aftermath of a star's long life. Not an explosion, not a catastrophe, but a slow unraveling, a star releasing its outer self into the dark, leaving something small and luminous at its core. A slow unraveling, releasing everything outward, and at the center, something small and bright remains. The interstellar medium, the space between stars, is not truly empty. It is filled with an extremely thin mixture of gas, dust, cosmic rays, magnetic fields, and the echoes of ancient stellar explosions. The density of this material varies enormously, from the hot, thin plasma of supernova remnants to the cold, dense cores of molecular clouds. On average, there is roughly 1 atom per cubic centimeter in the interstellar medium, which sounds like almost nothing, but adds up to an enormous amount of mass when spread across the billions of light-years of a galaxy. This material is the raw stock from which all future stars will form. Every atom expelled by a dying star enriches it slightly. Every supernova seeds it with new elements. The interstellar medium is a slow and patient reservoir, holding the material of past stars in readiness, waiting for gravity to gather it again into something new. The space between the stars is not empty. It is patient, holding everything that was and everything that will be. The Milky Way itself is a stellar nursery at the largest scale. It is a barred spiral galaxy, meaning it has a central bar-shaped region of stars from which 2 or more spiral arms extend outward. Our solar system sits in one of those arms, about 26,000 light-years from the galactic center. Star formation in the Milky Way is most active in the spiral arms, where the gas is densest, and where spiral density waves periodically compress the interstellar medium. If the Milky Way were a city, our sun would be a single street lamp in a quiet suburb, far from the bright and busy downtown of the galactic center. We are on the calm, outer edge of a vast rotating disk of 400 billion stars, orbiting the galactic center once every 230 million years. The last time our solar system was in this exact position in the galaxy, the dinosaurs had not yet evolved, and before that, not even complex life existed on Earth. We orbit the slow heart of our galaxy, one quiet lamp among 400 billion, returning to the same point once every 230 million years. Globular clusters are ancient, densely packed collections of stars, typically containing between 10,000 and several million stars in a sphere only a few hundred light-years across. They orbit the Milky Way like slow satellites, hanging in the galactic halo above and below the plane of the disk. They are old, some of the oldest structures in the universe, with ages up to 13 billion years, nearly as old as the universe itself. Looking at a globular cluster through a telescope is like looking back in time. The stars inside formed in the very early universe, from gas that had barely been enriched by previous stellar generations. In the core of a dense globular cluster, stars are packed so tightly that if our sun were at the center of one, the nearest star would be about a light-year away, instead of the 4 light-years to Proxima Centauri today. Old, dense, orbiting slowly, they are the quiet elders of our galaxy. Ancient beyond measure, orbiting slowly above the galactic plane, the elders of a galaxy that is still young by cosmic standards. The search for stars outside our galaxy has given us some of the most humbling numbers in science. The observable universe contains roughly 2 trillion galaxies. Each galaxy contains, on average, hundreds of billions of stars. The total number of stars in the observable universe is estimated at around 1 sextillion, a 1 followed by 21 zeros. This number is so large that every metaphor we reach for collapses under its weight. There are more stars in the observable universe than there are grains of sand on every beach and desert on Earth, multiplied by roughly 10,000. And yet, in the vast majority of the space that those stars inhabit, there is almost nothing. The stars are bright, but the dark between them is so much larger that the universe is, in the most literal sense, mostly emptiness. Most of existence is dark. The lights are rare. That makes each one matter more, not less. Even now, as you drift, the lights are outnumbered by the dark, and the dark makes them more visible, not less. The way stars move within a galaxy is one of the quieter puzzles of modern astronomy. In our solar system, objects further from the sun move more slowly. Mercury races around the sun in 88 days, while Neptune takes 165 years. You might expect the same pattern to hold in a galaxy. Stars near the outer edge should orbit more slowly than stars near the center, but they do not. Stars at the outer edges of galaxies orbit at roughly the same speed as those near the center, and in some galaxies, even faster. This is one of the key pieces of evidence for dark matter, an invisible, undetected form of matter that must make up most of the mass of galaxies to explain the way their stars move. Without it, galaxies would fly apart. With it, they are held together by something we cannot see, cannot touch, and cannot yet explain. The galaxy holds together, quietly, by something invisible. We are grateful, even if we do not fully understand why. The galaxy holds together by something we cannot see. Invisible, patient, ancient scaffolding in the dark. Rogue stars travel alone through the dark between galaxies, untethered to any galaxy's gravitational embrace. They are stars that have been flung outward through gravitational interactions, most often by the supermassive black holes at the centers of galaxies, which can accelerate individual stars to speeds of thousands of kilometers per second. A star moving at that speed could cross the entire Milky Way in only a few 100 million years, and then continue outward into the enormous void between galaxies, traveling in the dark, alone, for trillions of years. These hypervelocity stars will eventually cool redden, and fade without ever passing close to another star or planet. Their light will travel outward in all directions through the void, growing fainter with distance, reaching nothing. They are among the loneliest objects we have ever imagined, bright and moving, and completely alone, in the deepest dark between the island universes. A quiet light, moving alone through the void between galaxies, patient and ancient, and very, very far from anything. Open clusters are younger and looser than globular clusters, and they tell a different kind of story about the galaxy. They are groups of stars that form together from the same molecular cloud within the last few 100 million years, still bound loosely by mutual gravity, but slowly being pulled apart by the tidal forces of the Milky Way. The Pleiades, visible from anywhere on Earth during winter nights in the northern hemisphere, is perhaps the most familiar open cluster, a loose gathering of a few hundred stars about 400 light-years away, blue-white and young in stellar terms, only about 100 million years old. Ancient cultures around the world, Greek, Aboriginal Australian, Japanese, Aztec, gave the Pleiades special names and wove them into myths and calendars. Long before anyone knew what stars were made of, those particular 7 lights gathered in the winter sky and meant something. We have been watching them quietly for longer than we have been writing things down. Something ancient looked up at the same 7 lights and felt the same slow pull of wonder that you feel tonight. The concept of the stellar main sequence is not simply a category, it is a lifespan. Stars enter the main sequence when they begin stable hydrogen fusion and leave it when their core hydrogen is exhausted. The time they spend on the main sequence is called their main sequence lifetime, and it ranges from a few million years for the most massive stars to trillions of years for the smallest red dwarfs. Our Sun is roughly halfway through its main sequence lifetime of 10 billion years. It entered the main sequence about 4.5 billion years ago, and in about another 5 billion years, it will leave it and begin expanding into a red giant. Everything that has ever happened on Earth, every mass extinction and evolutionary leap, every civilization and every quiet night, has occurred in the first half of the Sun's main sequence life. We are at the midpoint of our star's working years. It is an oddly comforting thought, like being told you are exactly halfway through a long and quiet journey. We are halfway through our star's long life, enough behind us to feel ancient, enough ahead to feel unhurried. The distance light travels in 1 year, 1 light year, is approximately 9.5 trillion kilometers. The nearest star to our Sun, Proxima Centauri, is about 4.25 light years away. This means that the light reaching your eyes, when you look at Proxima Centauri, left that star over 4 years ago. You are not seeing the star as it is. You are seeing it as it was. When you look at the Andromeda Galaxy with the naked eye, a faint smear of light in the autumn sky, you are seeing light that left it 2.5 million years ago. At the time that light departed Andromeda, our ancestors were using stone tools and had not yet discovered fire. The sky is not a window to the present. It is a slow archive of the past, lit by ancient signals crossing the dark, still arriving after journeys measured in millions of years. Every star you have ever seen is a message from the past, a slow and patient letter, written in light, arriving long after it was sent. Wolf-Rayet stars are massive, hot, and dying. They represent the final phase in the life of the most massive stars, objects that began their lives 25 times the mass of the Sun or more, and have spent millions of years burning through their hydrogen so quickly that they have stripped away their own outer envelopes through intense stellar winds. What remains is a hot, bare core of helium and heavier elements, blazing at temperatures of 50,000 degrees or more, surrounded by an expanding shell of ejected material. Wolf-Rayet stars are among the most luminous objects in the Milky Way, sometimes millions of times brighter than the Sun. They are also among the shortest lived. A Wolf-Rayet star may remain in this phase for only 100,000 years before its core collapses in a hypernova, one of the most energetic events in the known universe. They are brief and brilliant and profligate, stars burning through everything they have, quickly, at the very end. The most brilliant ones burn fastest, and then, quietly, they give everything back to the dark. Eta Carinae is one of the most massive and unstable stars in our galaxy. It is a binary system, with a primary star roughly 150 times the mass of the Sun, located about 7,500 light-years away in the Carina Nebula. In 1843, it briefly became the second brightest star in the sky, even though it is thousands of light-years away, an outburst so powerful that it released as much energy as a typical supernova, without actually destroying the star. It ejected several solar masses of material in that event, forming the Homunculus Nebula, a pair of expanding lobes of gas and dust still visible today through telescopes, growing slowly outward from the star, like slow smoke from a fire that never quite went out. Astronomers believe Eta Carinae will eventually explode in a hypernova, potentially producing a gamma-ray burst. When it does, it will be visible in daylight from Earth. But this will not happen tonight. Tonight it simply glows, unstable and ancient, 7,500 years of light away. Something enormous is waiting to end, and the light of that waiting has been traveling toward us for 75 centuries. The Chandrasekhar limit is one of the most beautiful results in theoretical physics. In 1930, a 20-year-old Indian physicist named Subrahmanyan Chandrasekhar, traveling by steamship from India to England, calculated the maximum mass a white dwarf could have before it would collapse further under its own gravity. He worked through the equations by hand on the crossing. The answer, about 1 4/10 times the mass of our Sun, has since been confirmed by observation and is now called the Chandrasekhar limit. A white dwarf below this mass will cool quietly for trillions of years and eventually become a dark, inert remnant. A white dwarf above this mass, whether it formed that way or accumulated enough material from a companion star, will collapse in a type Ia supernova, a number calculated by a student on a ship crossing the ocean between one chapter of his life and the next, turned out to describe the fate of more stars than we will ever count. A young mind on a dark ocean worked out, in quiet numbers, the weight at which a star must fall. The question of whether there is life around other stars begins, necessarily, with the question of whether those stars have planets capable of supporting it. The zone around a star where liquid water could exist on a planet's surface is called the habitable zone, or sometimes the Goldilocks zone. Not too hot, not too cold, but just right for liquid water. For our Sun, this zone falls roughly between the orbits of Venus and Mars, a narrow band where Earth sits comfortably. For a red dwarf, the habitable zone is much closer to the star, because red dwarfs emit far less energy. A planet in a red dwarf's habitable zone might complete an orbit in only a few weeks. Whether such planets can be truly habitable, given the intense flares red dwarfs sometimes produce, is still an open question. But habitable zones exist around most stars. The geometry of warmth is common in the universe. What lives within that warmth remains one of the most quietly profound open questions we carry. Somewhere in the dark, another warm planet circles another quiet star, and we do not yet know what that means. The process of stellar evolution can be thought of as a slow and continuous exchange of energy and matter with the surrounding galaxy. Stars are born from the interstellar medium. They fuse lighter elements into heavier ones. They return enriched material to the interstellar medium through stellar winds, planetary nebulae, and supernovae. That enriched material mixes into the surrounding gas and dust, and eventually finds its way into the next generation of star-forming clouds. Each generation of stars is slightly more chemically complex than the last. The galaxy is gradually building a richer and richer vocabulary of elements, not through any plan or purpose, but through the patient repetition of the same cycle, billions of times over billions of years. You are made of elements that pass through the interiors of stars that lived and died long before our sun existed. The atoms in your hands right now have each had their own long journey through the cosmos. Tonight, while you breathe slowly, the atoms that make you are resting after journeys, measured in billions of years. The concept of look-back time gives astronomical observation a temporal depth that ordinary experience cannot easily accommodate. When we observe a galaxy 1 billion light-years away, we are seeing it as it was 1 billion years ago. When we observe a galaxy 10 billion light-years away, we are watching events that occurred when the universe was only a few billion years old. The James Webb Space Telescope has observed galaxies so distant that their light has been traveling for more than 13 billion years. Light that set out when the universe was less than 300 million years old. These distant objects show us a universe in its infancy, galaxies forming for the first time, stars igniting in pristine gas clouds that have never been enriched by previous stellar generations. We are looking at the beginning of the story, and we are reading it from near the end of the same chapter. The universe was young once, and we can still see it, faintly, at the very edge of the dark. We can still see the universe as it was in its infancy, a faint and ancient glow at the very edge of the observable dark. Stellar populations are a framework astronomers use to understand the age and composition of stars in different parts of a galaxy. Population I stars, like our Sun, are young and metal-rich. They formed from gas already enriched by many generations of stellar evolution, and they tend to be found in the spiral arms of galaxies, where star formation is most active. Population II stars are older and metal-poor. They formed earlier in the galaxy's history, from less enriched gas, and they tend to be found in the galactic bulge and in globular clusters. A theoretical population III, the very first stars, forming from pure hydrogen and helium, has not yet been directly observed, though some indirect evidence for them may exist in the signatures left in ancient gas clouds. Each population is a chapter in the galaxy's autobiography, written in the composition of its stars, a slow record of everything that came before, preserved in the light of every sun still burning. A galaxy writes its own history in the chemistry of its stars, slowly, across billions of years, in a language made of light. The way a star's mass determines its fate is one of the most elegant patterns in astrophysics. Stars below about 8 solar masses end their lives as white dwarfs, the cooling remnants of sun-like stars. Stars between roughly 8 and 20 solar masses end in core collapse supernovae, leaving behind neutron stars. Stars above about 20 to 25 solar masses may form black holes after their cores collapse, objects so dense that nothing, not even light, can escape their gravity. The boundaries between these fates are not perfectly sharp. They depend on mass, rotation, magnetic fields, and other factors still being studied. But the broad pattern is clear. Small stars die quietly, cooling over trillions of years into darkness. Medium stars die in brilliant but brief explosions and leave behind spinning remnants. The largest stars collapse into something from which nothing returns. Mass is destiny. It is the one quantity a star is assigned at birth, and it governs everything that follows, quietly and completely. From the first moment of collapse, the end is already written, quietly, in the mass of a star. The Hertzsprung-Russell diagram, revisited from a different angle, tells us something about time. When you plot the stars of a cluster on the diagram, the shape of the distribution tells you how old the cluster is. In a young cluster, you see stars across the full main sequence, including hot, blue O and B stars. In an old cluster, those bright, short-lived stars are gone. They have evolved off the main sequence. The point where stars begin to turn off the main sequence in a cluster is called the main sequence turn-off point, and its position tells you precisely how long the cluster has been burning. It is a stellar clock, precise enough to date clusters within a few % of their true age. By reading the turn-off points of globular clusters, we can determine that the oldest ones formed more than 13 billion years ago, nearly as old as the universe itself. The stars themselves have been keeping time all along. and we simply had to learn how to read their quiet record. The stars have been keeping time since before we existed, quietly, in their own language, waiting for us to learn to read it. The concept of a stellar black hole is one of the most quietly profound in all of science. When the most massive stars collapse, the resulting core is so dense that its gravity overwhelms every known force, the nuclear pressure that holds neutron stars together, the electromagnetic repulsion that keeps ordinary matter from compressing further. The collapse continues past the neutron star stage and forms a singularity, a point of infinite density where our understanding of physics breaks down completely. Surrounding the singularity is the event horizon, the boundary beyond which nothing can escape. Not matter, not light, not any signal of any kind. Whatever falls past the event horizon is, from our perspective, simply gone. Black holes do not destroy matter so much as they remove it from the universe we can observe. They are not voids. They are the densest possible concentrations of gravity, sitting silently in the dark, invisible except by their effects on the space around them. They are patient, and they are permanent, and they wait without needing to wait for anything. A still point in the dark where nothing escapes, silent, invisible, and infinitely patient. Stellar winds are not unique to our sun. Every star in the universe emits a constant outflow of charged particles from its surface, driven by the pressure of its radiation and the complex behavior of its outer layers. In our solar system, the sun's solar wind creates a bubble of influence, called the heliosphere, which extends out well past the orbit of Pluto and acts as a shield against some of the galactic cosmic rays that would otherwise reach the inner solar system. The Voyager probes, launched in 1977, crossed the boundary of the heliosphere, the heliopause, and entered interstellar space, becoming the first human-made objects to leave the sun's sphere of influence. They are still traveling, slowly, sending back faint signals from beyond the edge of everything we once called home. The heliosphere is not a wall. It is a soft, constantly fluctuating boundary, the last reach of our sun's breath, extending quietly into the dark between the stars. The last reach of the sun's breath extends into the dark, a soft and moving boundary at the edge of everything familiar. Among the rarest and most sought-after observations in modern astronomy is the direct imaging of exoplanets, planets orbiting other stars. The challenge is extraordinary. A planet is billions of times fainter than its host star and sits right next to it in the sky. Early exoplanet detections used indirect methods, measuring the tiny dimming of a star as a planet passed in front of it, or detecting the slight gravitational wobble a planet induces in its star's motion. The Kepler Space Telescope, launched in 2009, detected thousands of exoplanets using the transit method, confirming that planets are extraordinarily common. Most sun-like stars appear to have planetary systems. Most stars in the galaxy likely have planets. We are no longer wondering whether planets exist beyond our solar system. We are asking which ones might be warm and wet and alive. That question is still open, still quiet, still drifting through the dark, like a slow and patient signal waiting to be answered. Quietly, the cosmos holds billions of worlds, and the question of which ones are inhabited drifts unanswered through the dark. Supernovae are among the most energetic events in the known universe, but they are invisible to the naked eye in most cases. Their light, spread across tens of thousands of light years, arrives at Earth too faint to see. The last supernova, visible to the naked eye in the Milky Way, occurred in 1604, observed by Johannes Kepler, and it was briefly brighter than every star in the sky. Before that, Tycho Brahe observed one in 1572. These events, separated by decades, occurring in galaxies that contain hundreds of billions of stars, show how rare they are in any given galaxy. We expect roughly 1 or 2 supernovae per century in a typical galaxy like the Milky Way. Astronomers monitor thousands of other galaxies for supernovae, and they detect hundreds every year across the universe. The universe is always losing stars somewhere. Somewhere, always. Something enormous is ending, quietly. At distances so vast, the light takes thousands of years to reach us. Somewhere in the universe, a star is ending tonight, and the light of that ending will not reach us for thousands of years. The cosmic distance ladder is the system by which astronomers measure distances across the universe. Its first rung is parallax, the tiny shift in a nearby star's apparent position as Earth moves around the Sun. The second rung uses Cepheid variable stars, stars that pulsate with a period directly related to their luminosity, allowing their true brightness to be calculated, and thus their distance inferred. The third rung uses Type Ia supernovae as standard candles for the farthest distances. Each method builds on the one below it, and the accuracy of measurements at cosmic scales depends on the calibration of measurements at smaller ones. Edwin Hubble used Cepheid variables in 1923 to prove that the Andromeda Galaxy lay outside the Milky Way, a discovery that expanded the known universe overnight, from a single galaxy to a cosmos of billions. Before that night, most astronomers believed the Milky Way was the entire universe. The universe has been quietly larger than we thought at every stage of our understanding. At every step of understanding, the universe has turned out to be older, larger, and quieter than we imagined. The expansion of the universe means that the most distant galaxies are not simply far away. They are moving away from us, and the farther they are, the faster they recede. This is not because they are moving through space. Space itself is expanding, carrying galaxies with it. Beyond a certain distance, the cosmic event horizon, galaxies are receding faster than the speed of light, and their light will never reach us. They exist, but we will never see them. There are regions of the universe that are permanently hidden from us, not by any obstruction, but by the geometry of an accelerating expansion. The observable universe is not the whole universe. It is the portion of the universe whose light has had time to reach us in 13.5 billion years. Everything beyond that horizon exists in a silence and a darkness that we will never pierce, no matter how large we build our telescopes. The universe is larger than what we can know. There is something deeply calming in that. Beyond the edge of everything we can observe, the universe continues, vast and dark, and quietly beyond our reach. The relationship between stars and the planets around them extends to chemistry in remarkable ways. The composition of a star's atmosphere reflects the composition of the protoplanetary disk from which its planets formed. Stars with higher abundances of elements like magnesium, silicon, and iron are more likely to have rocky terrestrial planets similar to Earth. Stars with unusual chemical compositions may form planets with very different internal structures. More or less iron, more or less water, rock with different mineral compositions. The chemistry of life as we know it, carbon, hydrogen, oxygen, nitrogen, phosphorus, sulfur, was seeded in the protoplanetary disks of sun-like stars through the same nuclear processes that made those stars shine. The fact that life on Earth is made of the most common reactive elements in the universe is either a profound coincidence or a deep truth about the relationship between stars and complexity. We do not yet know which. We drift toward the answer, slowly. The elements that make life are the same elements stars make most easily, a quiet, ancient, and possibly deliberate rhyme. In the center of our galaxy, roughly 26,000 light-years away, sits a supermassive black hole called Sagittarius A star. It contains about 4 million times the mass of our Sun, compressed into a region smaller than our solar system. We cannot see it directly. The galactic center is obscured by thick clouds of gas and dust in visible light, but we have observed it in radio waves, X-rays, and infrared light. In 2022, the Event Horizon Telescope collaboration released the first direct image of the radio emission surrounding Sagittarius A star, a glowing ring of superheated gas spiraling around the black hole's event horizon, resembling in structure the image of the black hole in the galaxy M87, published 3 years earlier. At the center of the image, in the dark region where no light escapes, is the most massive object in the Milky Way. It sits there, always, in the dark center of our galaxy, quiet and enormous, while everything else turns slowly around it. Quietly, the cosmos moves around you. At the center of our galaxy, 4 million suns worth of gravity holds everything in a slow, ancient orbit. Dark matter accounts for roughly 27% of the total energy content of the universe. Ordinary matter, everything we can see, touch, measure, and detect, makes up only about 5%. The remaining 68% is dark energy, the unknown quantity driving the universe's accelerating expansion. Dark matter is invisible. It emits no light, absorbs no light, and interacts with ordinary matter only through gravity. We infer its existence from the way galaxies rotate, the way light bends around galaxy clusters, and the large-scale structure of the universe. Every simulation of how galaxies form and evolve, without dark matter, produces a universe that looks nothing like the one we live in. With dark matter included, the simulations match the observed universe with extraordinary precision. Something invisible is holding the cosmos together. We do not know what it is. We know only that without it, the lights would not be where they are, and the dark would be very different. We live inside a structure held together by something we cannot see, invisible and ancient, patient beneath everything that exists. The Magellanic Clouds are 2 irregular dwarf galaxies, visible from the southern hemisphere with the naked eye, the Large Magellanic Cloud and the Small Magellanic Cloud. They orbit the Milky Way and are being slowly consumed by it, their stars and gas gradually pulled into our galaxy's gravitational embrace over billions of years. The Large Magellanic Cloud, about 160,000 light-years away, is one of the most active star-forming regions in our galactic neighborhood, containing the Tarantula Nebula, the largest and most productive stellar nursery in the local group of galaxies. In 1987, a star in the Large Magellanic Cloud exploded as supernova 1987A, the first naked-eye supernova in 4 centuries, and astronomers detected not just its light, but a burst of neutrinos that arrived a few hours before the visible light, traveling unimpeded through the collapsing star's outer layers. 2 companion galaxies drifting nearby, one of them briefly announcing a stellar death across 160,000 years of dark. 2 small galaxies drift slowly beside us, slowly being gathered in, one of them briefly lit by a star's ancient ending. The life cycle of stars and the life cycle of galaxies are deeply intertwined. Young, gas-rich galaxies form stars rapidly. As stars age and explode, they heat and enrich the surrounding gas, and the feedback from those explosions can slow new star formation. Over billions of years, a galaxy's star-forming rate tends to decrease as it consumes and disperses its gas supply. Elliptical galaxies, which are older and smoother than spiral galaxies, have largely finished forming stars. They are quieter, redder, and more diffuse galaxies in old age. Spiral galaxies like the Milky Way are still in a productive middle phase, still making stars in their arms, still turning their gas into light. The universe's total rate of star formation peaked about 10 billion years ago and has been declining ever since. We live in the long, slow afternoon of the universe's creative period, past the frenetic morning, still before the quiet evening when the last stars form. We live in the slow afternoon of the universe's long creative life, past the peak, but still burning, still making light. The universe is estimated to be about 13.8 billion years old. The first stars formed when it was only a few 100 million years old, a cosmic infancy, relatively speaking. Our sun formed when the universe was about 9 billion years old. Humans, in any recognizable form, have existed for only the last 300,000 years, a fraction of a fraction of a percent of cosmic time. If the universe's history were compressed into a single year, humans would appear in the last 15 seconds of December 31st. All of recorded human history, every civilization, every book, every song, every quiet night, would fit inside the last blink of that final second. We are extraordinarily new. The universe was ancient before we drew our first breath. And yet, here we are, lying quietly in the dark, thinking about it, which is the most remarkable thing of all. In the last fraction of a second of cosmic time, something woke up and looked at the sky with wonder. Rest here for a moment. The universe is patient, and there is still more to come. The silence between galaxies is not a void, it is a structure. When astronomers map the large-scale distribution of galaxies across the universe, they find that galaxies are not scattered randomly. They cluster along thin filaments and sheets of dark matter, surrounding enormous empty regions called cosmic voids. These voids can be hundreds of millions of light-years across, volumes of space so empty that they contain almost no galaxies at all. The filaments connecting the galaxy clusters form what is called the cosmic web, and it is the largest known structure in the universe. The pattern resembles, in a way that is hard to dismiss as coincidence, the structure of neurons in a living brain, branching, connected, vast. Whether that resemblance carries any meaning beyond the mathematics of self-similar structures, no one can say. But the universe, at its largest scale, is not a smooth and featureless dark. It is intricately shaped, slowly assembled over billions of years, by the patient accumulation of gravity along invisible threads. The largest structure in the universe was built without a plan, by gravity alone, slowly, over billions of years, into something that almost looks like thought. When a star dies and scatters its material outward, that material does not immediately become part of a new star. It first becomes part of the interstellar medium, the thin, complex mixture of gas and dust that fills the space between stars. There it cools and mixes with older material, enriching it chemically. Over millions of years, turbulence, gravity, and the shock waves of other supernovae redistribute this material across the galaxy. Eventually, it may find its way into a dense molecular cloud, where it can participate in the slow process of collapse. The time between a star's death and the moment its expelled material is incorporated into a new star can be hundreds of millions of years. The iron in our blood, forged in the core of a dying star billions of years ago, spent an enormous amount of time drifting in the cold dark before it was gathered into our solar system's forming cloud. It was patient in the dark. It had no choice but to be. The iron that makes your blood red drifted through the cold between the stars for hundreds of millions of years before it found its way here. The process by which heavy elements are synthesized in stars is called stellar nucleosynthesis, and it is one of the most satisfying explanations in all of science, the kind that, once you understand it, makes the world feel more complete. In the first few minutes after the Big Bang, the universe made only hydrogen, helium, and trace amounts of lithium. Everything else, every element on the periodic table beyond those, was made inside stars. Carbon, the backbone of all organic chemistry, is forged in the cores of red giants through the triple alpha process, in which 3 helium nuclei fuse together. Oxygen, nitrogen, neon, and silicon are forged in successively hotter and denser stellar cores. Iron is the end product of stellar fusion, the element at which fusion stops releasing energy, and the heaviest elements, from gold to uranium, are forged in the extreme conditions of neutron star mergers and supernova explosions. Every element that exists beyond helium was assembled inside a star and returned to the universe through that star's death. Every element that makes the world complex was assembled inside a star and returned to the cosmos through its ending, quietly and completely. Neutron star mergers are among the most violent and most creative events in the universe. When two neutron stars orbit each other in a binary system, they slowly spiral inward as they radiate energy in the form of gravitational waves, ripples in the fabric of space-time itself. Over millions of years, this inward spiral continues until the two stars finally collide and merge in an event called a kilonova. In the extreme heat and neutron density of that collision, the rapid neutron capture process, called the R process, forges heavy elements in vast quantities. In 2017, astronomers detected both the gravitational waves and the electromagnetic afterglow of a kilonova for the first time, in an event called GW170817. The spectral analysis of its light confirmed the presence of gold, platinum, strontium, and other heavy elements being created in real time, 130 million light-years away. The gold in every ring on every finger on Earth was made in an event like that. Two dead stars, circling each other for millions of years, finally meeting in the dark. Two silent, spinning remnants of dead stars circled each other for millions of years before colliding, and in that one moment made all the gold in the world. Gravitational waves were predicted by Albert Einstein in 1916 as a consequence of his general theory of relativity, but they were not directly detected until 2015, nearly a century later. The detection was made by the LIGO interferometers, instruments so sensitive they can measure a displacement smaller than 1/10,000th the diameter of a proton across a 4-kilometer baseline. The signal detected on September 14, 2015, lasted only a fraction of a second and corresponded to the merger of two black holes about 1.5 billion light-years away. The gravitational waves from that merger passed through the Earth in the same moment, imperceptibly stretching and compressing the fabric of space-time, including everything on and in the Earth, including every sleeping person on the planet that night. We did not feel it. Nothing felt it. The universe shuddered quietly, passed through us, and continued on its way without needing our notice. A ripple in space-time passed through the Earth while everyone slept, through every body, every bed, every dreaming mind, and no one felt a thing. The formation of binary star systems from a single collapsing cloud is a process still being studied in detail. When a rotating cloud collapses, conservation of angular momentum causes it to spin faster as it contracts, and the resulting disk of material can fragment into two or more centers of collapse rather than one. This fragmentation is common enough that binary and multiple star systems are the majority, rather than the exception, among sun-like stars. In some cases, the two protostars remain bound together for their entire lives, orbiting in a stable embrace for billions of years. In others, dynamical interactions within the forming cluster can separate them, leaving each to travel alone. The question of whether our Sun was once part of a binary system is one that astronomers have considered seriously. There is evidence in the orbital architecture of our solar system, particularly in the distribution of distant comets, that a companion may once have existed, long since lost to the dark. Perhaps the Sun once had a companion, lost so long ago that nothing remains but a faint hint in the orbits of distant, cold ice. The Orion Molecular Cloud Complex is not just a nebula. It is a vast, interconnected system of molecular clouds, active star-forming regions, and young stellar populations spread across hundreds of light-years in the constellation Orion. The Orion Nebula, visible with the naked eye, is merely the brightest and most photogenic part of a much larger structure. Embedded within the complex are dozens of star-forming regions at different stages of development, from cold, dark clouds that have barely begun to collapse, to young clusters already clearing away their natal gas. The stars of Orion's belt, Alnitak, Alnilam, and Mintaka, are young, hot, and massive. Born from the same complex only a few million years ago, they will live short lives, burn brilliantly, and explode within the next few million years, seeding the complex with new elements and possibly triggering the next round of star formation. The same clouds that made the stars of Orion are still making new ones tonight. The same ancient cloud that made the bright stars of Orion is still making new ones tonight. Quietly, in the dark, between the familiar lights. Stars do not only influence their immediate surroundings. Through the mechanism of galactic winds, the combined output of thousands of supernovae in a galaxy's most active star-forming regions can drive enormous outflows of gas and dust out of the galaxy entirely. These galactic winds can heat and enrich the circumgalactic medium, the diffuse halo of gas surrounding a galaxy, and can even slow or stop the infall of new material available for star formation. In the most extreme cases, in compact galaxies undergoing very rapid star formation called starbursts, the galactic wind can be visible as a bipolar outflow extending for tens of thousands of light-years above and below the galaxy's plane. The Cigar Galaxy, Messier 82, shows exactly this, a striking image of red filaments of hydrogen gas streaming outward from both poles of the galaxy, driven by the collective energy of thousands of supernovae happening in a relatively short period. A galaxy catching its breath after too much creation, quietly exhaling into the surrounding dark. Even galaxies need to breathe, slowly exhaling into the dark after long periods of making too many stars too quickly. The question of when the universe will form its last star is one of the most distant and quiet questions in cosmology. As the universe continues to expand, the gas available for star formation is gradually consumed or dispersed. The rate of star formation has been declining for 10 billion years and will continue to decline. Theoretical models suggest that the universe will effectively stop forming new stars in about 100 trillion years, 10,000 times the current age of the universe. After that point, only the longest-lived red dwarfs will still be burning. All the brighter stars, all the stars that have ever been visible to human eyes, will long since have died. The sky, in that far future, will contain only faint red points of light, fewer and fewer, cooling slowly across an expanding dark. The universe has a very long twilight ahead of it. We are living, right now, in the brilliant early morning of that twilight, surrounded by more light than will ever exist again in the same abundance. We are living in the brightest era the universe will ever know, and it is already slowly, quietly dimming. When we think about the scale of stellar time, our own lives become something tender and precise. A human life of 80 years is to the main sequence lifetime of our sun as a single second is to roughly 2 years. In the lifetime of the universe, a human life is less than a blink. And yet, in that blink, we have learned the composition of stars, mapped the structure of the cosmos, detected gravitational waves from 1 billion light-years away, and built instruments cold enough and patient enough to see the first light of the first galaxies. In the briefest possible window of cosmic time, something small and warm and fragile looked out at the universe and began, slowly, to understand it. That is not nothing. That is, in the context of 13 billion years of mostly silent physics, something quietly extraordinary. A universe briefly looking at itself through the eyes of something it made by accident, lying still, breathing slowly, in the dark. In the smallest imaginable sliver of cosmic time, the universe made something that could wonder at it, quietly, briefly, and with great tenderness. The stars we see with our naked eyes on a clear night number only about 5 to 10,000 from any given location on Earth. This represents a vanishingly small fraction of the 400 billion stars in the Milky Way, and an even more vanishingly small fraction of the stars in the universe. The vast majority of stars are invisible to us, too faint, too distant, obscured by gas and dust, or simply beyond the physical limits of what our eyes can gather. The sky we see is not the sky that exists. It is a sparse and incomplete sample, a handful of the brightest and nearest lights, selected by the limits of human biology. The real sky, the full sky, is almost entirely dark to our unaided senses. We have been navigating and dreaming by a fraction of all the light there is. For as long as we have been human, the universe has always been more than we could see, always darker, always deeper, always holding more than it has ever shown us. The night sky we know is a sparse and imperfect sample. The full sky is immeasurably richer and darker than anything our eyes can hold. The role of supernovae in shaping the chemical evolution of galaxies cannot be overstated. Each core collapse supernova ejects between 1 and 10 solar masses of newly synthesized elements into the interstellar medium: oxygen, magnesium, silicon, sulfur, calcium, and iron, among others. Over the lifetime of a galaxy, the cumulative effect of billions of supernovae is to gradually enrich the interstellar medium, raising the metallicity of gas available for subsequent star formation. This is why younger stars tend to have higher metallicities than older ones. It is also why the solar system's composition, with its abundance of oxygen, silicon, and iron, reflects the enrichment history of this part of the Milky Way over its first 9 billion years. Every supernova is a gift to the future, an investment in the complexity of stars and planets and chemistry that have not yet formed. The explosions are violent, but their legacy is quiet and slow and constructive, the universe building toward something richer, one death at a time. Every explosion in the history of the cosmos has made the future slightly more complex, quietly, one death at a time. Some stars live such short lives that they are born and die within the same molecular cloud that created them. The most massive O-type stars, with lifetimes of only a few million years, can complete their entire existence, from protostellar collapse to supernova explosion, before the cloud that birthed them has fully dispersed. These stars light up their own birth clouds from within, ionizing the surrounding gas and creating what are called HII regions, glowing clouds of ionized hydrogen that blaze with the characteristic red light of hydrogen emission. When one of these massive stars explodes, the shock wave can compress the surrounding cloud, triggering the formation of the next generation of massive stars in almost the same location. It is a relay, a chain of creation and destruction, each generation lighting the fuse of the next, in a sequence that can continue for tens of millions of years before the cloud is finally dispersed and the region goes quiet. A chain of creation, each generation lighting the next. And then, slowly, the cloud disperses and the region grows quiet again. The color of nebulae in photographs is partly real and partly a translation. Nebulae emit light at very specific wavelengths, corresponding to the electron transitions of particular atoms: hydrogen, oxygen, sulfur, nitrogen. Some of these wavelengths are visible to the human eye, and some are not. When astronomers photograph nebulae with narrowband filters, filters that pass only light from specific atomic transitions, they capture far more detail than broadband imaging allows. The famous Hubble palette assigns the emission of sulfur to red, hydrogen to green, and oxygen to blue, producing images of extraordinary color and detail that are scientifically accurate, but not what a human eye would see in person. The real visual appearance of most nebulae to the naked eye, if you could somehow stand close enough, would be dimmer, less saturated, mostly red and pink. The brilliant images we know are a kind of translation, the universe's chemistry rendered visible in colors our minds can hold, which is a form of honesty, even if it is not a literal one. We translate the universe into colors our minds can hold, which is a form of honesty, even if it is not the whole truth. The discovery of exoplanets has transformed our understanding of planetary formation, and by extension, stellar formation. Before the Kepler mission, launched in 2009, we knew of fewer than 400 exoplanets. By the end of its mission in 2018, Kepler had confirmed more than 2,000, with thousands more awaiting confirmation. The TESS mission, which followed, expanded the search to a wider area of sky. We now know that planets are not rare exceptions. They are the norm. Most stars have planets. Small, rocky planets appear to be the most common type, and the diversity of planetary systems discovered has been far wider than anyone anticipated. Planets orbiting multiple stars, planets with years lasting only a few days, planets of pure water, planets with no star at all, drifting free in the dark. The galaxy is full of worlds we have never imagined, arranged around suns we have barely begun to study, in configurations that continue to expand what we think is possible. The galaxy is full of worlds we have not yet imagined, drifting quietly around their suns, in the dark, uncounted and unhurried. The heliosphere, the bubble of solar wind inflating around our solar system, is not perfectly spherical. As our solar system moves through the local interstellar medium at roughly 20 kilometers per second, the heliosphere is pushed and shaped by the pressure of interstellar gas flowing past it, forming a blunt leading edge called the heliopause bow region and a long, trailing tail. The exact shape of the heliosphere is still being determined from the data returned by the Voyager probes and the IBEX mission. One of the more poetic aspects of this picture is that our entire solar system, all its planets, all its moons, all its comets and asteroids, and the thin light of the sun, is enclosed inside this vast, moving bubble of solar breath, traveling together through the galaxy. Everything we have ever known, every planet we have ever visited, every probe we have ever launched, exists inside a single soap bubble of magnetism and charged particles, drifting slowly through the dark between the stars. Everything we have ever known exists inside a single bubble of solar breath, drifting slowly through the dark between the stars. The concept of stellar age gradients in galaxies gives us a window into how galaxies grow. In the Milky Way, the oldest stars are concentrated in the central bulge and the halo, where star formation was most intense in the galaxy's youth. The younger stars, including our Sun, tend to be in the disk, and particularly in the spiral arms, where gas has continued to flow, and star formation has continued to operate over the galaxy's entire history. This creates a quiet gradient across the galaxy, a slow transition from ancient, metal-poor stars near the center to younger, metal-rich stars in the outer disk. If you could travel from the galactic center outward to our position, you would pass through billions of years of stellar history, from the oldest surviving lights of the early universe to stars that formed only millions of years ago. The galaxy is not uniform. It is layered, like the rings of a very old tree, each layer telling a different chapter of the same slow story. The galaxy is layered in time, ancient at the center, younger at the edges, a slow and patient record of its own becoming. As our understanding of star formation has deepened, it has become clear that the process is neither perfectly efficient nor perfectly predictable. Only a small fraction of the mass in a molecular cloud, perhaps 1 to 10%, actually ends up in stars. The rest is dispersed by the feedback from newly formed stars, returned to the interstellar medium, or simply never reaches the density needed to collapse. This inefficiency is not a flaw in the system. It is what prevents galaxies from consuming all their gas in a single rapid burst of star formation and then going dark. The inefficiency of star formation is, in a very real sense, the reason the universe has been making stars for 13 billion years, rather than a few hundred million. The universe does not rush. It uses a little of what it has, slowly, over time, in a process that is sustainable precisely because it wastes most of what it could use. There is something gently wise in that, though it knows nothing of wisdom. The universe wastes most of what it could use, and in doing so, ensures there is always more to make, slowly, and for a very long time. The term stellar archaeology describes the practice of studying the chemical composition of old stars to reconstruct the history of the early universe. The most ancient stars, found in the halos of galaxies and in globular clusters, carry in their atmospheres a chemical record of the conditions present when they formed, including the compositions of the first supernovae that enriched the gas from which they condensed. By analyzing the spectra of these ancient stars with high-resolution spectrographs, astronomers can infer the properties of population 3 stars that exploded long before any instrument existed to observe them directly. The echoes of the first stellar deaths are preserved in the oldest surviving lights. The galaxy is an archive of its own history, and its oldest stars are the most ancient chapters, written in the language of chemistry, slowly cooling in the halo, still carrying a record of a universe we will never directly see. The oldest stars are the universe's most ancient libraries, cooling slowly in the dark, still carrying the records of a beginning we can only read in their light. The way our sun will die is, by stellar standards, among the gentler endings. In about 5 billion years, as its core hydrogen is exhausted, the sun will begin fusing hydrogen in a shell around the core, causing the outer layers to expand slowly outward. Over the following few billion years, the sun will become a subgiant, then a red giant, expanding to perhaps 100 to 200 times its current size. The inner planets, Mercury, Venus, and possibly Earth, may be consumed. Whether Earth is engulfed or merely scorched depends on precisely how far the expansion reaches and how much mass the sun loses as it expands. After the red giant phase, the sun will shed its outer layers in a slow stellar wind, forming a planetary nebula visible perhaps 10,000 light-years away. At its center, the white dwarf remnant of our sun will cool over billions of years in the dark, slowly fading, quietly releasing the last of its warmth into the space that was once its home. Our sun will end slowly and gently, not in an explosion, but in a long, quiet exhale, leaving only a pale and cooling ember in the dark. The light we see from stars arrives in fragments across time. The sun's nearest neighbor, Proxima Centauri, shows us a past 4 years old. The Andromeda Galaxy shows us a past 2.5 million years old. The cosmic microwave background, the faint glow of heat left over from the Big Bang, shows us a past 13.8 billion years old. It is the oldest light we can observe. It comes from everywhere in the sky simultaneously, at a temperature just 2.7 degrees above absolute zero, carrying information about the state of the universe when it was less than 400,000 years old. We exist at a particular moment in an unfolding cosmic story, surrounded on all sides by echoes from every stage of the universe's past. The present is a thin skin over a very deep history. Everything we see when we look up is, in some measure, the past arriving. We are surrounded on all sides by the past, light from every era of the universe, arriving slowly from every direction in the dark. The physics of light bending around massive objects, gravitational lensing, was predicted by Einstein and confirmed during the 1919 solar eclipse, when Arthur Eddington observed that the positions of stars near the sun's edge were shifted by exactly the amount relativity predicted. Gravitational lensing has since become one of the most powerful tools in astronomy. Massive galaxy clusters act as natural lenses, bending and amplifying the light of galaxies behind them, allowing us to see objects too faint and too distant to observe otherwise. Einstein rings, perfect circles of lensed light around a foreground mass, are among the most visually striking phenomena in the observational universe. The James Webb Space Telescope has produced images in which dozens of gravitationally lensed arcs and rings are visible in a single field. Gravity does not just pull things together. It bends the light of everything behind them, turning the universe's most massive objects into vast, curved windows onto the deeper dark. The universe uses its own gravity as a lens, bending ancient light around massive objects, letting us see further into the dark than we could alone. There is something called the cosmic noon, the period roughly 10 billion years ago when the universe was forming stars at its peak rate, perhaps 10 to 30 times faster than the Milky Way does today. At that time, young galaxies were richly supplied with cold gas, and mergers between galaxies were more frequent, triggering enormous bursts of star formation. The night sky, had any observer existed then, would have blazed with far more young, hot, blue stars than we see today. The universe was younger, and more frenetic and more luminous in aggregate. Since then, the rate of star formation has declined by roughly a factor of 30. We live in a quieter era, an afternoon of gentle, ongoing creation after the bright frenzy of the morning has passed. The universe is still making stars, still building complexity, still turning gas into light. But it does so now with the patience and economy of something that has already done its most intense work and is not in a hurry to finish. The universe has already lived through its most frenetic morning, and now it works slowly, patiently, in the long and quiet afternoon of its making. The Milky Way and the Andromeda Galaxy are on a slow collision course. They are currently about 2.5 million light-years apart, and they are approaching each other at roughly 110 kilometers per second. In about 4.5 billion years, the two galaxies will begin to pass through each other, a process that counterintuitively will not cause individual stars to collide. Stars are so small relative to the distances between them that the two galaxies will largely pass through each other like two swarms of bees passing through each other, with almost no individual collisions. But the gravitational interactions will be profound. Gas clouds will be compressed, triggering new waves of star formation. The shapes of both galaxies will be dramatically distorted. Over the following few billion years, the two galaxies will merge into a single, larger elliptical galaxy, one that astronomers have already named Milkomeda. It will be quieter than either of its parents, its star formation largely complete, its arms dissolved into a smooth and ancient ellipse. In a few billion years, our galaxy will merge with another and become something quieter, a smooth and ancient ellipse, its creative days behind it. The idea that we are somehow separate from the cosmos, observers looking outward at a universe that does not include us, is one that the science of stellar formation quietly dissolves. We are not watching stars form from the outside. We are made of the same material. The carbon in your body was fused in the triple alpha process, inside a red giant star that died long before our sun formed. The oxygen you breathe was forged in a massive star's core and scattered in a supernova. The calcium in your bones was made in stellar explosions. The hydrogen in the water in your cells is as old as the universe itself, forged in the first few minutes after the Big Bang, 13.8 billion years ago. You are not a person looking at the universe. You are a temporary local arrangement of the universe, looking at itself. When the cosmos made you from its own material, after billions of years of patient work, so that it could briefly wonder what it is. You are the universe, temporarily arranged into something that can lie still in the dark and quietly wonder at its own existence. The question of why the universe has the particular physical constants it does, why gravity is exactly as strong as it is, why the speed of light is exactly as fast, why hydrogen is stable in the way it is one that physics cannot yet answer from first principles. What we can say is that if those constants were even slightly different, stars as we know them could not exist. If gravity were stronger, stars would burn through their hydrogen far too quickly to allow the long, slow stellar lifetimes that permit planetary systems to develop and complexity to emerge. If the strong nuclear force were slightly weaker, hydrogen nuclei could not fuse at all, and there would be no stars. The universe appears to be precisely tuned, in its most fundamental constants, for the existence of stars. Whether this is coincidence, necessity, or something else entirely, is a question that the science of star formation places quietly and without urgency at the very deepest level of what we can ask. The universe is tuned for stars, and stars, it turns out, are tuned for everything else. The slow drift of a star through the galaxy over its lifetime is called its galactic orbit, and it is a journey of remarkable scale. Our sun orbits the galactic center at roughly 220 kilometers per second, completing one orbit every 225 to 250 million years. This period is sometimes called a cosmic year or a galactic year. In the roughly 4.5 billion years since our Sun formed, it has completed approximately 20 galactic orbits. In each of those orbits, it has passed through different regions of the galaxy, different densities of interstellar medium, different positions relative to the spiral arms, different proximity to star-forming regions and supernova remnants. The solar system has not sat quietly in one neighborhood. It has been slowly traveling through the galaxy for its entire existence, carried by its own momentum, in a vast and unhurried orbit, returning to approximately the same position every 225 million years, like a very slow clock, keeping a very long time. Our solar system has been slowly traveling through the galaxy for its entire existence, a quiet, unhurried orbit, returning to the same region every 200 million years. The stellar mass function, the distribution of stellar masses at birth, tells us something fundamental about the nature of complexity in the universe. Most stars are small. The peak of the stellar mass function lies well below the mass of our Sun. Most stars that form are dim red dwarfs, objects containing a fraction of the mass of our star. And yet it is the middle mass stars, the ones in the range of roughly half to a few solar masses, that appear best suited to hosting the kind of long-lived, stable planetary systems where chemical complexity can emerge over billions of years. Too massive, and the star burns out before planets have time to develop complex chemistry. Too small, and its habitable zone is so close that tidal locking and stellar flares may make life difficult. The Sun sits in what might be a particularly favorable range, not the most common type of star, not the most luminous, but perhaps among the most hospitable. We live around a quiet, middle-aged, middle-mass star, and that may not be a coincidence. We orbit a quiet, middle-aged star, not the most common, not the most brilliant, perhaps the most patient kind. The ancient light of the cosmic microwave background fills the entire universe, in every direction, at every moment. It is not a glow you can see. It falls in the microwave part of the spectrum, invisible to human eyes. But it is there, passing through everything, arriving from all directions with extraordinary uniformity. The tiny fluctuations in its temperature, variations of only 1 part in 100,000, encode the seeds of all the structure in the universe. Those tiny fluctuations were the regions of slightly higher density that eventually, through billions of years of gravitational collapse, became the filaments and galaxy clusters and individual galaxies and stars that fill the observable universe today. Every star that has ever existed grew, ultimately, from a small bump in the primordial fog, a barely perceptible density fluctuation in the earliest moments of the universe. We are the amplified echo of something almost imperceptibly small, made vast and complex by the patient work of time. Everything complex in the universe grew from a barely perceptible ripple in the first light, slowly, quietly, over all the time there has been. Somewhere in the Milky Way, right now, a star is being born, not in a flash, not with any fanfare, but slowly, in a cold, dark cloud. A protostar is warming in its dusty envelope. It has been collapsing for perhaps 100,000 years. In another 100,000, it may ignite. Its first light will not be visible to anyone. It will be locked inside layers of gas and dust for millions of years. When it finally clears its birth cloud and shines freely for the first time, its light will travel outward across hundreds of light years and eventually, perhaps, reach the instruments of some civilization we cannot yet imagine, in a time we cannot yet conceive. Nothing about this is urgent. Nothing about it is attended. It is simply the universe doing what it has always done, in the dark, with patience, without needing to be watched. It is enough that it happens. It has always been enough that it happens. The universe does not require an audience. The universe does not require an audience. It has been making stars in the dark for 13 billion years, quietly, because that is what it does. The word ancient, used again and again in any discussion of space, carries a weight that is hard to feel in ordinary life. When we say the universe is 13.8 billion years old, the number is too large to hold. But consider this. If every year of cosmic time were a single human breath, a slow breath, 4 seconds long, the age of the universe would take 1,775 years to breathe. The Roman Empire rose and fell in roughly 500 years. All of recorded human history fits inside a few hundred breaths of cosmic time. The sun formed after about 1,125 years of breathing. Life on Earth appeared after about 1,300. You, lying here, breathing slowly in the dark, your entire life, the whole of it, is a fraction of a single one of those cosmic breaths. And yet you are here, and you are conscious, and you are resting, and that is something the universe spent 13 billion years preparing for. You are one breath in an unimaginably long breathing, and you are here, and you are resting, and the universe made room for that. The night sky changes, on the longest time scales. The stars we see tonight are not the stars that ancient humans saw, in the sense that the constellations shift very slowly as the solar system moves through the galaxy, and as each star pursues its own slow orbit. In 100,000 years, the familiar shapes of Orion and the Big Dipper will be distorted beyond recognition. In 1,000,000 years, they will be gone entirely, replaced by new groupings of stars that no human civilization has yet named. The sky above us is temporary. The patterns we have drawn on it, the myths we have pinned to those patterns, belong to this narrow window of time. Our descendants, if they exist, will look up at a different sky and make different stories, and their descendants will look up at another. The sky is not fixed. It is a slow river, and we are looking at one moment in its current, and it is enough, more than enough, to be here for this one quiet moment of it. The sky we know is ours only for a little while, a slow river, and we are here for one quiet moment of its turning. The most distant object ever observed, as of the early 21st century, is a galaxy designated JADES GS Z14-0, observed by the James Webb Space Telescope at a redshift corresponding to a look-back time of more than 13.5 billion years. The light from this galaxy left it when the universe was only about 300 million years old. The galaxy is surprisingly massive and luminous for its age, suggesting that stars formed very early and very quickly in the first structures of the universe, more quickly than many theoretical models predicted. It is a young galaxy, seen in the universe's infancy, already shining with the light of billions of newly formed stars. That light has been traveling for more than 13 billion years to reach us. It entered the James Webb Space Telescope's mirror on a quiet night in the recent past, and was processed and confirmed and shared with the world. And now it is part of what we know, an ancient signal, received at last. A light that has been traveling for over 13 billion years arrived quietly, recently, at a cold mirror floating in the dark, and we saw it. The shapes of spiral galaxies are created and maintained by what are called spiral density waves, patterns of slightly enhanced density that rotate through the galactic disk more slowly than the stars themselves. As stars and gas clouds pass through a density wave, they are temporarily compressed, which can trigger star formation. This is why the brightest stars in a spiral galaxy tend to be found in the arms. They were born there, in the compressed gas of the density wave, and they are so short-lived that they die before they can drift far from where they formed. The arms of a spiral galaxy are not made of the same stars over time. They are more like a slow wave on the surface of water. The wave has a shape, but the water molecules beneath it are always moving, always changing. The galaxy's arms are a pattern, not a population. They are the galaxy breathing, slowly, in a rhythm older than any star that now lives inside them. The spiral arms are not made of fixed stars. They are a slow, ancient breathing pattern, and the stars move through them like breath itself. The oldest light we can see with our own eyes on any clear night is not from a distant galaxy. It is from the Andromeda Galaxy, 2.5 million years old, just barely visible as a smear in the autumn sky. But the oldest object you can see with the naked eye, in the form of a single point of light, is the star Deneb, in the constellation Cygnus. Deneb is so luminous, perhaps 100,000 times brighter than the sun, that it remains visible, despite being roughly 2,000 light-years away. The light reaching your eyes from Deneb tonight left that star roughly 2,000 years ago, during the height of the Roman Empire. You are seeing the past of a star so luminous, it could be seen from 2,000 light-years away, by human eyes alone, unaided, on a quiet night. You have always been able to look into deep time with nothing more than your own eyes. You just had to know where to look. With nothing but your own eyes, on any clear night, you can look 2,000 years into the past. A quiet, ancient light, free to anyone who looks up. There is a place in the Milky Way called the Galactic Habitable Zone, the range of distances from the galactic center where conditions are thought to be most favorable for life. Too close to the center, and the density of stellar explosions and intense radiation would make it difficult for complex chemistry to persist on a planetary surface. Too far out, and the lower abundance of heavy elements would make rocky planets rare, and carbon chemistry less available. Our solar system sits comfortably within the galactic habitable zone, not too close to the dangerous center, not too far from the enriched disk. We are in a quiet neighborhood of the galaxy, in a region where stellar density is moderate, where supernovae are not too frequent, where the interstellar medium has been enriched enough to make rocky planets common. We are, in the broadest sense, in a good location. Placed here, not by any choice, but by the slow, orbital dynamics of a forming galaxy that happened to carry our sun's birth cloud to this particular quiet place. We drifted here, carried by the slow orbit of a forming galaxy, and we arrived in a quiet neighborhood, precisely suited for what we became. The light of the very first stars, population 3 stars, has never been directly observed. It is one of the great missing chapters in the universe's story. These stars formed in the first few 100 million years of the universe, from pure hydrogen and helium, and were so massive and luminous that their radiation fundamentally changed the cosmos, ionizing the neutral hydrogen gas that had filled the universe since the recombination epoch. This period, called the Epoch of Reionization, ended the cosmic dark ages, the long period after the Big Bang, during which no stars yet existed, and the universe was filled only with dark, neutral gas. The James Webb Space Telescope is pushing back toward this epoch, studying the earliest galaxies whose light was shaped by the first generation of stars. We have not yet seen the first stars themselves. They burned too briefly and too long ago. But we are reading their signatures in the galaxies that came after, the way you might read a person's character in the lives they shaped. We have never seen the first stars. They burned too briefly and too long ago, but we read them in everything they left behind. The universe contains structures called magnetars, neutron stars, black holes, white dwarfs, brown dwarfs, red giants, supergiants, protostars, and 100 other kinds of object we have names for. It also certainly contains objects we do not yet have names for, forms of matter or energy or structure that have not yet been discovered, waiting in parts of the electromagnetic spectrum we do not yet observe, or in regions of space we have not yet reached, or in phenomena that have not yet been noticed, because no one has looked in quite the right way. Every generation of astronomers has discovered objects that the previous generation could not have named. There is no reason to think we are the first generation to have found everything. The universe is not finished revealing itself. In the dark beyond the edge of what we know, there are things waiting quietly, patient as all the dark things are patient, for the moment when someone finally looks in the right direction and sees them clearly for the first time. Beyond what we know, in the dark, Things wait patiently, as all the dark things have always waited, to be seen. Lie still for a moment. Let the universe be large. It does not need you to hold it together tonight. The stars are forming, slowly, in cold clouds, in the dark, in the spiral arms of galaxies too distant to see. The oldest stars in the galaxy are cooling quietly in the halo, carrying the chemistry of a universe we will never directly see. The sun is burning steadily, without effort, in the same slow fusion it has maintained for 4.5 billion years. The Earth is turning, gently, at 1,000 miles per hour, and you feel none of it. You are still, riding the spin of a planet, in orbit around a star, in a spiral arm of a quiet galaxy, in a local group of galaxies, in a supercluster, in a filament of the cosmic web, in the vast and ancient universe that made everything you are from things it had already made before. You are inside the universe completely. There is no outside. There is no distance between you and the cosmos. You are one of its temporary arrangements, a brief, warm pattern in the dark. The iron in your blood was forged in the heart of a dying star. Not metaphorically, not poetically, literally. The iron atoms in your hemoglobin, the ones that carry oxygen through your body as you breathe right now, were synthesized in the core of a massive star that lived and died long before our sun existed. That star collapsed and exploded, and its iron scattered outward into the interstellar medium, and over hundreds of millions of years it drifted in the cold dark, and eventually it gathered with other material into the cloud that formed our solar system, and from that material the Earth was built, and from the Earth life emerged. And in the long, slow process of biological evolution, something learned to use that iron to carry oxygen through living bodies. And here you are, breathing slowly, eyes closed, the iron of a dead star doing quiet work inside you, as it has done every moment of your life. You are, in the most literal and patient sense, a child of the stars. And not because the phrase is beautiful, though it is, because it is true. The universe is very old, you are very new, and yet you are made of the same things. Hydrogen as ancient as the Big Bang itself. Heavier elements forged across billions of years of stellar birth and death, assembled on a small warm planet, orbiting a quiet star, in a calm corner of a spiral galaxy. The distance between you and the farthest star is enormous, and yet, chemically, structurally, in the most fundamental sense, there is no distance at all. You are made of the same matter. You follow the same physical laws. The gravity that holds galaxies together holds you to your bed tonight with the same quiet authority. Let the weight of the universe rest on you gently. Let it hold you down. Let your body be heavy and still. You do not need to go anywhere. The cosmos is very large, and it has been here for a very long time, and it will continue long after this night has passed into morning. You are a brief and tender thing, inside something immense and ancient and ongoing, and there is nothing required of you tonight but to breathe and to rest and to let the quiet dark hold you. The stars are patient. The dark is patient. The long, slow turning of the galaxy goes on without any effort from you at all. Let your breath slow. Let the thoughts soften at their edges and drift, the way starlight drifts, the way cold gas drifts in the long dark between the stars, slowly losing its shape, dispersing gently into something wider and calmer and less defined. There is nothing to solve tonight. There is nothing to hold. The universe has been solving itself, quietly and without hurry, for 13 billion years, and it does not need your help this evening. You are resting in the middle of something ancient and vast, and deeply, quietly beautiful. I hope you sleep well tonight and dream softly. Good night. The universe contains more possible star formations than there are atoms in the observable universe. This is not hyperbole. It is a consequence of the combinatorial mathematics of how gas clouds collapse, how their turbulence distributes mass, how magnetic fields thread through them, how nearby stellar feedback arrives from different angles and intensities, and how the thousands of variables involved in each collapse interact. No two stars form in identical circumstances. Every star that has ever existed, every one of the estimated 1 sextillion, arrived through a unique set of conditions. A slight difference in the original turbulence of the cloud, a slightly different magnetic field orientation, a shock wave that arrived 1,000 years earlier or later. Each star is, in this technical and quiet sense, singular. The universe has never repeated itself, not once, in the making of a light. It has made 1 sextillion unique things, each one burning for its allotted time, and then gone. The universe has made 1 sextillion unique lights, no two the same, and it has done this quietly, without any plan, across all the time there has been. Variable stars are stars whose brightness changes over time, and they come in dozens of distinct types, each with its own mechanism and its own rhythm. Cepheid variables pulsate. Their outer layers expand and contract in a regular cycle, brightening and dimming over periods of days to weeks. RR Lyrae variables do the same over shorter periods. Long-period Mira variables are red giants that pulsate over months, their brightness changing by factors of hundreds. Eclipsing binaries dim and brighten as one star passes in front of the other. Flare stars, mostly red dwarfs, brighten suddenly and unpredictably as magnetic energy is released from their surfaces. The night sky, observed carefully over weeks and months, is not static. It breathes and flickers and pulses. Some of this variation is slow and rhythmic, like a heartbeat. Some is sudden and irregular. The sky we see on any given night is a single frame in a long, slow film, and the film has been playing since long before anyone was watching. The sky breathes and pulses on timescales longer than a human attention span, a slow film, playing since long before there were eyes to watch it. The detection of neutrinos from supernova 1987A was one of the most important observations in the history of astrophysics. Neutrinos are nearly massless particles that interact so weakly with matter that they pass through the entire Earth as if it were not there. In the few seconds of a stellar core collapse, more energy is released as neutrinos than our Sun will release in its entire 10 billion year lifetime. When the star in the Large Magellanic Cloud collapsed on February 23, 1987, neutrino detectors buried deep underground in Japan, the United States, and the Soviet Union simultaneously registered a burst of 24 neutrinos over about 13 seconds, 24 particles out of the trillions that passed through each detector. The rest passed through the Earth without a trace. They passed through you, if you had been alive and standing in the right location. A dying star sent its final signal outward in all directions through the dark, and the universe received it in almost perfect silence, the way all the deepest messages are received. A dying star sent its final message in particles that pass through everything, and the universe received it almost in silence, the way the deepest things always arrive. The stellar metallicity of our Sun is unusually high compared to many stars of similar age in our region of the galaxy. This has led some astronomers to suggest that the Sun may have formed in a part of the galaxy closer to the center, where enrichment from earlier generations of stars was more advanced, and gradually migrated outward to its current position over billions of years. Stellar radial migration, as this process is called, is now understood to be common. Stars do not stay in fixed orbits. Gravitational interactions with spiral density waves and molecular clouds can alter their orbits over millions of years, moving them inward or outward by thousands of light years. Our Sun may have begun its life in a richer, busier region of the galaxy and drifted slowly outward to the quieter neighborhood it occupies today. If this is true, then we are, in a gentle sense, immigrants, born closer to the center, traveled outward over billions of years to find a calmer place to spend our star's long middle life. We may have begun somewhere busier and drifted slowly outward, the Sun finding its calm neighborhood over billions of years of quiet wandering. The concept of the cosmic abundance of elements, the proportion in which different elements exist throughout the universe, is one of the most elegant results of combining nuclear physics with observational astronomy. Hydrogen makes up roughly 74% of all ordinary matter in the universe by mass. Helium makes up about 24%. All other elements combined, every atom of carbon, oxygen, nitrogen, iron, gold, and everything else on the periodic table, make up the remaining, roughly 2%. We live on a planet of rock and water and air, made almost entirely of what the universe considers rare. The silicon in the Earth's crust, the oxygen in the oceans, the iron in the core, all of it belongs to that 2% minority. The vast, overwhelming majority of the universe is hydrogen and helium. The simplest things, the oldest things, the raw material from which everything else was painstakingly assembled, one stellar generation at a time. Everything complex in the universe is made from the rarest 2%, quietly assembled over billions of years from the simplest things that exist. The rotation of a molecular cloud before it collapses determines, in large part, the shape of the planetary system that forms around the resulting star. Even a very slow rotation, far too slow to be perceptible over human timescales, becomes significant once the cloud has collapsed by a factor of millions. Conservation of angular momentum means that as the cloud shrinks, it spins faster, and this spin flattens the collapsing material into a disk. The disk shape is not arbitrary. It is the direct geometric consequence of the original rotation, preserved and amplified through the collapse. The plane of our solar system, the flat disk in which all the planets orbit, is a memory of the slow spin of the cloud that formed the Sun, preserved across 4.5 billion years. When you picture the solar system as a flat, spinning disk, you are picturing the shape of a rotating gas cloud that existed before the Sun, translated into the geometry of worlds. The flat disk of our solar system is a memory of a slow rotation in a cold gas cloud, a shape preserved across 4.5 billion years. Some of the most isolated stars in the universe exist in the vast spaces between galaxies, the intergalactic medium. These stars, called intracluster stars or intergalactic stars, were stripped from their host galaxies during gravitational interactions and now float in the emptiness between galaxy clusters. They are not part of any galaxy. They orbit no galactic center. They drift in a darkness so profound and so empty that the nearest other star may be millions of light years away. Their night sky, if a planet orbited one of them and something lived on it, would show only a faint, distant haze of galaxy clusters rather than the rich band of the Milky Way. They are the most solitary lights in the universe, adrift in the largest voids, burning quietly in a dark that almost nothing else inhabits, circling nothing, belonging to no system, patient in a solitude deeper than anything we can imagine from our position inside a galaxy teeming with light. The loneliest stars in the universe belong to no galaxy, drifting in the dark between the island universes, circling nothing, quietly burning alone. The process of accretion, the gradual accumulation of mass through gravity, is not unique to star formation. It is the universal mechanism by which the cosmos builds its large structures, from dust grains to planets, to stars, to galaxies, to galaxy clusters. At every scale, the same patient process operates. Small things attract slightly smaller things, grow slightly larger, attract more, grow larger still. A dust grain in a protoplanetary disk accumulates other grains. A planetesimal sweeps up smaller bodies. A protoplanet clears its orbital path. A galaxy pulls in smaller satellite galaxies. A galaxy cluster draws in individual galaxies from the surrounding filaments. The same logic, gravity, rewarding what is already large, operates from the scale of microns to the scale of hundreds of millions of light years. The universe has one primary tool for building things. It gathers what is already there, slowly, patiently, without urgency, and it has been doing this since the first density fluctuations of the early universe gave gravity something to work with. The universe has one tool for building everything. It gathers what is already there, slowly, at every scale, without urgency. Circumstellar disks around young stars are not static. They are alive with motion, dust grains spiraling inward, gas flowing in complex patterns, pressure waves rippling outward, gaps opening where young planets have cleared their orbits. Astronomers using the ALMA radio telescope, an array of 66 high-precision antennas in the Atacama Desert of Chile, have imaged dozens of these disks in extraordinary detail, revealing ring-like structures, spiral arms, gaps, and asymmetries that correspond to forming planets and the physical processes of disk evolution. One of the most iconic images produced by ALMA shows the disk around the young star HL Tauri, a system only about 1 million years old, already showing multiple distinct rings and gaps carved by bodies that may be the earliest stage of planetary formation. We are watching, in real time, the beginning of what could become a solar system. Every ring in that image is a story still being written, slowly, in dust and gravity and light, around a star younger than the dinosaurs. Around a star younger than the dinosaurs, planets are already carving their paths through the dust, quietly writing the first lines of a very long story. The temperature at the center of our sun, approximately 15 million degrees Celsius, is hot enough to fuse hydrogen, but, remarkably, is actually lower than the temperature that classical physics alone would predict is needed for fusion. The quantum mechanical phenomenon of quantum tunneling allows hydrogen nuclei to fuse even at temperatures below the classical threshold, by tunneling through the energy barrier that would otherwise prevent their nuclei from getting close enough. Without quantum tunneling, the sun would not shine. Our existence depends on one of the most subtle and strange features of quantum mechanics, the ability of particles to pass through barriers they classically cannot surmount. The sun does not shine because its core is hot enough in a classical sense. It shines because reality at the smallest scales is strange enough and gentle enough and patient enough to find a way through barriers that should, by the ordinary rules, be impassable. The sun shines because the universe found a quiet way through a barrier that should have been impassable, gently, at the smallest possible scale. The solar wind carries information. The charged particles streaming outward from the sun at 400 to 800 kilometers per second carry with them a record of the sun's magnetic activity, its cycle of sunspots and solar flares, its periods of calm and its periods of turbulence. When these particles reach Earth, they interact with the magnetic field and create the aurora borealis and aurora australis, the northern and southern lights. The auroras are not random. They are a direct visual translation of the sun's magnetic state at the moment the particles left its surface, rendered in light by the Earth's magnetic field. A quiet aurora means a quiet sun. An intense aurora means an intense burst of solar activity. The lights dancing in the polar sky are a message from our star, encoded in charged particles, decoded by our atmosphere in colors of green and red and violet. A slow, ancient, and beautiful correspondence between the Earth and the sun. The northern lights are a message from the sun, decoded by our atmosphere in color. A slow and beautiful correspondence across 93 million miles of dark. The interiors of stars are, in a very real sense, opaque. A photon of light generated in a nuclear reaction in the sun's core does not travel outward in a straight line. It is immediately absorbed by the dense plasma and re-emitted in a random direction, then absorbed again, then re-emitted again. This process, called a random walk, means that the photon's journey from the core to the surface is not a straight path, but a wandering, zigzagging, back and forth process that takes an average of between 100,000 and 1 million years to complete. Once the photon reaches the surface, however, It escapes into space in about 8 minutes and 20 seconds to reach the Earth. The light warming your face on a summer afternoon spent the better part of 100,000 years making its way to the surface of the Sun, and then crossed 93 million miles of vacuum in slightly over 8 minutes. The vast majority of its journey was the slow part. The crossing of space was almost instantaneous by comparison. Light spends 100,000 years wandering to the surface of the Sun, and then crosses 93 million miles of space in 8 minutes. The slow part was always the inside. Stellar oscillations, the subtle ringing of stars like enormous cosmic bells, have given rise to a field called astroseismology. Stars oscillate in response to pressure waves moving through their interiors, and these oscillations cause tiny, regular variations in their brightness and their spectral lines. By analyzing these variations with high-precision photometry, astronomers can infer the internal structure of stars, the size of their cores, the depth of their convection zones, their rotation rates at different depths, with a precision that no other method can provide. The Kepler Space Telescope was particularly valuable for this work, observing hundreds of thousands of stars continuously for years and detecting oscillations in thousands of them. Our Sun oscillates too. It rings at many frequencies simultaneously, each one probing a different depth. The Sun is always singing, quietly, in pressure waves that take hours or days to complete a cycle, a slow, complex chord that tells us what is happening inside a place we will never directly observe. The Sun is always ringing, quietly, in pressure waves that take hours to complete, a slow, complex chord carrying news from its unreachable interior. The fate of a star cluster is written in time. When a cluster of stars forms from a single molecular cloud, its stars share a common birthplace, a common age, and broadly similar chemical compositions. Over time, dynamical interactions between stars in the cluster, the gravitational pushes and pulls of close encounters, gradually redistribute energy among the stars. The most massive stars slow down and sink toward the center of the cluster, while lighter stars are accelerated outward toward the edges. Eventually, some stars gain enough energy to escape the cluster entirely. This process, called evaporation, slowly depletes the cluster's membership over hundreds of millions to billions of years. Open clusters, being loosely bound, evaporate relatively quickly. The Pleiades, for instance, will likely be dispersed in another 200 to 250 million years. The stars of the Pleiades that now huddle together in the winter sky will one day drift apart, each traveling alone through the galaxy, carrying only the same birth chemistry as quiet evidence of their shared origin. The stars of the Pleiades will drift apart over the next few 100 million years, sharing nothing in the end but their chemistry and a long-forgotten beginning. The magnetic activity cycle of the Sun, the roughly 11-year cycle of sunspot activity, solar flares, and coronal mass ejections, is driven by the interaction between the Sun's differential rotation and its magnetic field. The Sun does not rotate as a solid body. Its equator rotates faster than its poles, a period of about 25 days at the equator versus 35 days at the poles. This differential rotation stretches and tangled the magnetic field lines threading through the Sun, building up magnetic energy over years. Eventually, this stored energy erupts in concentrated regions of intense magnetism called sunspots, dark, cool spots on the surface where the magnetic field suppresses convection. The cycle of winding and releasing takes about 11 years on average. Astronomers have records of sunspot cycles going back centuries, and tree ring and ice core data extend this record back thousands of years. The Sun has been keeping its own quiet rhythm for as long as we have been here to notice it. The Sun has been keeping its own quiet 11-year rhythm, winding and releasing, for longer than human memory reaches. Beyond the edge of the observable universe, the cosmos almost certainly continues. The observable universe, the sphere of space whose light has had time to reach us in 13.8 billion years, has a radius of about 46 billion light-years. But the total universe is likely far larger and may be infinite. Some cosmological models suggest that the universe is not just large, but genuinely without edges, not bounded by a wall or a surface, but simply continuing in all directions without limit. In an infinite universe, everything that can happen does happen, somewhere, an infinite number of times. Every arrangement of matter and energy, every configuration of stars and planets and chemistry, exists somewhere beyond the horizon we can observe. The portion of the universe we can see is not special. It is one quiet sample of something so vast that the idea of its size dissolves the moment you try to hold it. And that dissolution, that gentle failure to comprehend, is perhaps the most honest response the mind can have. Beyond the edge of what we can see, the universe almost certainly continues, vast, in a way that dissolves every attempt to hold it, quietly and completely. The concept of a standard candle in astronomy, an object whose true luminosity is known, allowing its distance to be measured from its apparent brightness, represents one of the most elegant practical solutions in science. The underlying principle is simple. If you know how bright something truly is, you can calculate how far away it must be to appear as faint as it does. Cepheid variables were the first standard candles to be systematically used, and their calibration by Henrietta Swan Leavitt in the early 20th century was one of the great scientific achievements of the era. Leavitt, working as a human computer at the Harvard Observatory, noticed that Cepheid variables with longer pulsation periods were intrinsically more luminous, a relationship so precise and so consistent that it could be used as a cosmic measuring tape. Her discovery made it possible to measure distances to other galaxies and ultimately to determine the scale of the universe. A woman measuring the brightness of stars on glass photographic plates in a room without a telescope changed our understanding of the size of everything. A woman measuring stars on glass plates without a telescope established the scale of the observable universe, quietly, in a room, with patient attention. The chemistry of the interstellar medium is surprisingly complex. In the cold, dark cores of molecular clouds, where temperatures approach 10 Kelvin and densities are high enough to shield molecules from the ultraviolet radiation that would otherwise destroy them, chemists have detected more than 250 distinct molecular species. Among them are simple molecules like water, carbon monoxide, and ammonia, but also more complex ones: ethanol, formaldehyde, acetaldehyde, and even glycine, the simplest amino acid, has been tentatively identified in some regions. These molecules form not in the gas phase, but on the surfaces of tiny dust grains, where atoms can stick and react, and slowly build complexity over thousands of years. The clouds where stars are born are not sterile environments. They are slow and cold chemical laboratories, assembling the precursors of biology before any star has ignited, in a darkness so complete that no light has ever touched most of it. The universe begins its chemistry long before it makes its lights. The universe begins its chemistry in the dark, before the stars, slowly building the pieces of life on the surfaces of cold dust grains, in the quietest places that exist. The way that planets form around a star is strongly influenced by the position of the snowline, the distance from the star beyond which water ice can remain stable in the protoplanetary disk. Inside the snowline, only rocky, refractory materials can condense into solid grains. Outside it, water ice and other frozen volatiles add to the available solid material, dramatically increasing the surface density of the disk and allowing much larger planetary cores to form. In our solar system, the snow line was located roughly between the orbits of Mars and Jupiter. This is why the inner solar system contains small, rocky planets: Mercury, Venus, Earth, and Mars, while the outer solar system contains the giant planets, which formed where icy solids were abundant enough to build the massive cores that then captured enormous envelopes of gas. The architecture of our solar system is, in part, a record of where water freezes around a young star, a line in space, drawn by temperature, that shaped everything that lives on this side of it. A line where water freezes around a young star divided the solar system into rock and ice, and on the warm side of that line, everything we know emerged. The Sagittarius dwarf galaxy is in the process of being consumed by the Milky Way. It is a small, elongated galaxy orbiting our own, and over billions of years, the Milky Way's tidal forces have stretched and torn it into a long stream of stars that now wraps around the galactic halo multiple times, a structure called the Sagittarius Stream. Stars from the Sagittarius dwarf are being incorporated into the Milky Way even now, becoming indistinguishable from native Milky Way stars over time. Some of the stars in our galaxy are immigrants, absorbed from smaller galaxies in the past. The Milky Way has been growing by accretion, gathering smaller galaxies and dissolving them throughout its history, and the chemical and kinematic signatures of those ancient mergers are preserved in the motions and compositions of stars scattered across the galactic halo. The galaxy we live in is partly assembled from things it consumed long ago, and it carries that history quietly in the orbits of stars that no longer remember where they came from. Some stars in our galaxy were born elsewhere, absorbed from smaller galaxies, their origins dissolved over billions of years into the slow memory of orbits. The Hubble constant, the rate at which the universe is currently expanding, has been the subject of a persistent tension in cosmology. Two independent methods of measuring it give slightly different answers. Measurements based on the cosmic microwave background give a value of about 67 kilometers per second per megaparsec. Measurements based on Cepheid variables and Type 1a supernovae in the local universe give a value of about 73. The discrepancy is small in absolute terms but statistically significant, and it has persisted as measurements have become more precise. It may indicate an error in one or both measurement methods, or it may indicate that our standard model of cosmology is missing something, some physical process operating in the early universe that we have not yet identified. Astronomers call this the Hubble tension, and it is one of the most actively discussed unsolved problems in modern physics. The universe is expanding, that much is certain. Exactly how fast, it has not yet finished telling us. The universe is expanding, but it has not yet finished telling us exactly how fast, a quiet discrepancy at the edge of what we know. The concept of a stellar population's turn-off age, the age at which the most massive stars still on the main sequence are found, is a tool of such elegant simplicity that it is easy to overlook how profound it is. By observing a cluster of stars and identifying where the most massive, brightest stars are beginning to leave the main sequence and evolve into giants, you can determine the age of the entire cluster. The most massive stars live the shortest lives, so whichever massive stars are still present tell you how long the cluster has been burning. Clusters with hot blue stars still on the main sequence are young. Clusters where only yellow and orange stars remain are old. The method works because all stars in a cluster formed at approximately the same time, and the passage of time is written in the gradual disappearance of the brightest, most impatient stars. The sky keeps its own quiet ledger of time, and the ledger is readable if you know where to look. Time writes itself into the sky in the gradual disappearance of the brightest stars. A quiet ledger, readable in light. Binary stars that are close enough to exchange material can create exotic and violent phenomena that isolated stars cannot. When one star in a binary evolves off the main sequence and expands into a red giant, its outer layers may overflow the gravitational boundary between the two stars, a surface called the Roche lobe, and flow toward the companion. If the companion is a white dwarf, this stream of material forms an accretion disk of hot gas around it, glowing in X-rays and visible light. The system is called a cataclysmic variable, and it can produce periodic brightening events called novae, not the catastrophic death of a supernova, but a runaway thermonuclear explosion on the surface of the white dwarf as accumulated hydrogen ignites. Unlike a supernova, the star survives. The outburst fades, the accretion resumes, and over thousands of years the cycle repeats. Two stars in a close orbit, sharing material, flaring quietly, in a rhythm that has been going on since long before anyone gave it a name. Two stars, sharing material across the dark between them, flaring and fading, flaring and fading, a slow and ancient rhythm no one was there to name. The discovery that the expansion of the universe is accelerating, made in 1998 by two teams of astronomers studying Type 1a supernovae, was awarded the Nobel Prize in Physics in 2011. It was one of the most unexpected results in the history of cosmology. Astronomers expected to find that gravity was slowing the expansion left over from the Big Bang. Instead, they found that distant supernovae were fainter than expected, meaning they were farther away than a decelerating expansion would place them. Something was pushing the universe apart, faster and faster. This unknown energy component, making up roughly 68% of the total energy content of the universe, was named dark energy. We do not know what it is. We know it exists, because without it, the supernovae data makes no sense. We know it is smoothly distributed throughout the universe. We know it has a consistent behavior over cosmic time. We know it will eventually drive all but the nearest galaxies beyond our observable horizon. And we know, quietly, that it is the dominant component of the universe, and we cannot explain it. The dominant substance in the universe, the thing that controls its ultimate fate, is something we cannot see, cannot explain, and cannot name beyond the label we gave our ignorance. The way sound cannot travel through space, because space is too thin for pressure waves to propagate, is one of the most quietly counterintuitive facts about the cosmos. In science fiction, explosions in space boom and roar. In reality, they are perfectly silent to any observer at a distance. The universe is mostly vacuum, and sound requires a medium. Closer to home, in the dense plasma of a stellar core, or the gas of a nebula, pressure waves do propagate, but at frequencies and on timescales so vast that no human ear could register them. The sun's oscillations, if translated into the human hearing range, sound like a deep, complex chord. The pressure waves, in a large molecular cloud, translated similarly, would be something far below the lowest note a bass voice can produce. The universe has a rhythm. It has its own slow music. It is simply played at frequencies too low and too slow for creatures as small and as brief as we are to hear. A music that has been playing for billions of years, in the dark, for no audience at all. The universe has always been playing its own slow music, in frequencies too low and too vast for anything as brief as us to hear. The light curve of a star, the way its brightness changes over time, is a record of everything that happens to or around it. A planet transiting in front of the star produces a regular, shallow dip. A flare produces a sudden brightening. An orbiting companion star produces a periodic dimming. A cloud of dust drifting across the star produces an irregular, asymmetric fading. The star, KIC 8462852, nicknamed Boyajian star or Tabby's star, produced a light curve so bizarre, with irregular, deep dips of up to 22%, that one early hypothesis, since largely discounted, involved an alien megastructure. The most likely explanation involves clouds of cometary dust, but the star still produces unusual dimming events that are not fully explained. The universe contains objects whose behavior does not yet fit neatly into any category. Things we are still watching, still measuring, still turning over in the slow, patient work of understanding. The sky is not finished being strange. It has not exhausted its surprises. The sky has not exhausted its surprises. There are still stars whose behavior we watch closely, quietly, without a complete explanation. The process by which molecular clouds are disrupted after star formation is as important to the galaxy's ecology as the formation process itself. Once massive stars ignite within a cloud, their radiation and winds begin to erode the surrounding gas. Over a few million years, the combined effect of ionizing radiation, stellar winds, and eventually supernova explosions clears away the remaining material, dispersing what was not incorporated into stars back into the interstellar medium. This dispersal is not wasteful. It is the mechanism by which the enriched material from the new stars is returned to the galaxy for future use. The molecular cloud that once existed in Orion's sword around the trapezium cluster is being slowly blown apart right now by the radiation of the young stars at its center. In a few million years, it will be gone, dispersed into the general medium of the galaxy, enriched slightly, waiting to be gathered again, somewhere else, in some future cloud, for some future generation of stars we will never see. Even now, the cloud that made the Orion Nebula's stars is being slowly scattered back into the galaxy, enriched, patient, waiting to be gathered again. The oldest stars ever discovered carry names that reflect their extremity. Stars with metallicities so low that they formed from gas barely touched by previous stellar generations are called extremely metal-poor stars, and the most extreme examples have iron abundances less than 100,000th of the Sun's. The star SMESIS J031300.36 670.839.3, discovered in 2014, has the lowest iron abundance of any star measured, so low that astronomers believe it formed from gas, enriched by the explosion of a single population 3 star, a direct chemical descendant of the very first generation of stars in the universe. These ancient stars are not unusual in appearance. They look like ordinary faint stars. They carry their extraordinary age in their chemistry alone, visible only through the analysis of their spectra. They are walking records of a universe we cannot observe directly, survivors of the first stellar generations, still quietly burning in the halo of the Milky Way, older than almost everything. In the halo of our galaxy, stars are still burning that formed from the ashes of the very first stars, patient survivors, carrying the chemistry of a universe we can no longer see.